Right now, as you sit there, 26,000 light years beneath your feet, at the exact center of our galaxy, something is glowing that should not exist. Hundreds of structures, thousands of them, stretching up to 150 light years into space. Perfectly organized, perfectly spaced, like the strings of a harp carved from the void itself. For 40 years, scientists have been staring at these filaments, and for 40 years, they have failed to explain what creates them. In 1984, astronomer Farhad Yousefzadeh pointed the Very Large Array at the galactic center and discovered giant threads of radio emission standing vertically through space. He assumed they were artifacts, glitches in the data, but when other telescopes confirmed the structures, when multiple wavelengths showed the same impossible formations, the scientific community realized they were looking at something real. Something that operates according to rules we do not understand. Then in 2022, the Meerkat telescope in South Africa revealed nearly 1,000 of these filaments pervading the core. And in 2023, Yousefzadeh discovered a second population, horizontal filaments, running parallel to the galactic plane. Pointing like arrows directly at Sagittarius A star, our galaxy's 4 million solar mass black hole, these are not clouds, they are not nebulae. They are structures, organized, magnetized, emitting synchrotron radiation from particles moving at 99.9% the speed of light. And we have no idea how they form. The year was 1984. Ronald Reagan was president. The Cold War was freezing the world into two armed camps. And in the high desert of New Mexico, the Very Large Array was scanning the heavens, 27 radio dishes working in concert to map the radio emissions bleeding from the center of our galaxy. Farhad Yousefzadeh was a young astronomer. He was working with Mark Morris and Don Chance, using the VLA to observe the galactic center at 20-centimeter wavelengths. They were looking for the usual suspects: supernova remnants, regions of star formation, the scattered bones of stellar death. What they found instead were lines, long, straight, impossibly organized structures that appeared to be standing vertically through the galactic plane. Radio-emitting threads that stretched for parsecs. That was 45 light years. Each thread was impossibly thin, just 0.02 parsecs wide. That is roughly 400 times the distance from Earth to the Sun, compressed into a thread that spanned 45 light years in length. The first reaction was denial. These could not be real structures, they had to be artifacts, glitches in the radio interferometry process. The Very Large Array is not a single telescope. It is 27 separate dishes spread across the plains of San Agustin, combining their signals through a process called aperture synthesis. Perhaps the combination algorithm had failed. Perhaps the phase calibration was wrong. Perhaps some systematic error in the data reduction pipeline had created these illusory threads where none existed. But the structures persisted when they reprocessed the data, when they observed at different wavelengths, when they used different calibration techniques. The filaments remained, stubborn, undeniable, staring back from the radio maps like scratch marks carved into reality itself. The paper that Yousefzadeh, Morris, and Chance published in Nature in August 1984 carried a carefully worded title: Large, highly organized radio structures near the galactic center. Not filaments, not threads, just structures, because they genuinely did not know what they were looking at. The abstract described radio continuum observations that revealed a remarkable group of linear features in the galactic center radio arc region. Linear, not filamentary, not thread-like, the language of scientists who cannot believe their own data. But the data was real. Other teams confirmed it. The Nobuyama 45-meter telescope in Japan saw them. The Molonglo Observatory Synthesis Telescope in Australia detected them. The Australia Telescope Compact Array mapped them in exquisite detail. These were not artifacts. They were genuine astrophysical structures, emitting non-thermal radio emission from a region of space that should not be capable of creating such perfectly organized forms. The scientific community called them non-thermal radio filaments, NTFs. That term, non-thermal, is critical. It means the emission is not coming from hot gas. Thermal emission comes from atoms and molecules at high temperatures, radiating energy as they collide with each other. Non-thermal emission comes from relativistic particles, electrons moving at speeds approaching the speed of light, spiraling through magnetic fields, radiating synchrotron emission as they curve through space. This immediately created a problem. Where were these relativistic electrons coming from? What was accelerating them to such absurd velocities? And why were they arranged in such precisely organized structures? For decades, the filaments remained an unsolved mystery. Astronomers studied them, mapped them, measured their spectral indices, their polarization properties, their magnetic field strengths. The original radio arc that Yusufzadeh discovered contained 10 individual filaments, each one parallel to its neighbors, each one stretching for parsecs through space, all of them perpendicular to the galactic plane, all of them emitting polarized synchrotron radiation indicating magnetic fields running along their lengths. But they were rare. In the 35 years following their discovery, astronomers identified only a handful of these structures scattered through the galactic center. Perhaps a dozen, maybe 2 dozen if you counted the faint ones. They were enigmatic, they were mysterious, but they appeared to be isolated curiosities, strange structures that defied explanation but were too few in number to represent a fundamental aspect of galactic center physics. Then came Meerkat, the radio telescope that changed everything. Meerkat sits in the Karoo Desert of South Africa's Northern Cape province. It is not one telescope. It is 64 separate radio dishes, each 13.5 meters in diameter, spread across an area 8 kilometers wide. It observes at frequencies between 0.58 and 14.5 gigahertz. That is wavelengths between 2 and 50 centimeters. Right in the sweet spot for observing synchrotron emission from cosmic ray electrons spiraling through magnetic fields. The telescope achieved first light in July 2016. By 2018, it was producing images of the galactic center with a sensitivity and resolution that exceeded anything previously achieved. Ian Haywood, an astrophysicist at the University of Oxford and Rhodes University, led the team processing the Meerkat Galactic Center mosaic. They spent 3 years analyzing 200 hours of observing time, building a radio map that covered 6 square degrees of sky. That is 30 times the area of a full moon, centered on the exact heart of our galaxy. When they published the image in January 2022, it revealed a universe of complexity that no one had suspected existed. The galactic center was not empty space punctuated by a few scattered sources. It was a battlefield, a war zone, a region of space so violent and so active that it glows across the entire electromagnetic spectrum. Supernova remnants appeared everywhere, the expanding shells of stars that died in catastrophic explosions. Some were old, faint, their shockwaves dispersing into the interstellar medium. Others were young, bright, still radiating furiously as their ejected material plowed through surrounding gas at thousands of kilometers per second. One supernova remnant at the edge of the mosaic was almost perfectly spherical, a rare geometric form that indicated it had exploded into a uniform medium. Most supernovae expand asymmetrically, shaped by density variations in their surroundings. This one had detonated in space that was somehow smooth, homogeneous, creating a bubble so perfect it looked artificial. Giant radio bubbles dominated the vertical structure. These had been discovered previously in 2019 by Haywood and Yusufzadeh using earlier Meerkat data. They extend for 1,400 light-years above and below the galactic plane, perpendicular to the disk, like chimneys venting energy from the core. Evidence of an explosive event several million years ago that pumped enormous quantities of energy out of the galactic center and into the surrounding halo. But the most shocking discovery was the filaments. Meerkat revealed not dozens of them, nearly 1,000. They were everywhere, pervading the entire galactic center region, arranged in groups, in clusters, in precisely organized formations that looked like nothing else in astronomy. Some ran perfectly parallel to each other, equally spaced, like the strings of a harp. Others twisted and curved, fragmenting and rejoining, creating loops and arcs that defied any simple geometric description. Yusufzadeh and his collaborators published their statistical analysis in the Astrophysical Journal Letters in February 2022. For the first time, they could study these structures as a population, not isolated curiosities, but a fundamental feature of the galactic center environment. They measured the lengths of the filaments, the orientations, the spacings between grouped filaments, the spectral indices that revealed how their radio brightness changed with frequency, the magnetic field strengths inferred from the synchrotron emission. The filaments ranged in length from a few parsecs to over 150 light-years. The longest ones towered above the galactic plane like radio skyscrapers. The shortest ones were still dozens of light-years long. All of them were thin, incredibly thin. The width measurements indicated structures less than 1 parsec across. That means these filaments have aspect ratios exceeding 100 to 1. They are not clouds, they are threads. One-dimensional structures stretched through three-dimensional space, and they are old. Yusufzadeh estimated that many of the filaments are approximately 6 million years old. That dating comes from the propagation speed of cosmic ray electrons combined with the measured lengths of the filaments. If electrons are traveling at close to light speed and the filaments are 100 light-years long, then the electrons have been traveling for at least 100 years. But synchrotron losses cause the electrons to radiate away their energy over time. The oldest electrons visible in the radio maps must have been accelerated roughly 6 million years ago. Before that time, they would have lost so much energy they would no longer emit detectable radio waves. 6 million years ago, our hominin ancestors were just beginning to split from the lineage that would become chimpanzees. The Earth had no humans, no agriculture, no cities, no civilization. And at the center of our galaxy, something was pumping relativistic electrons into magnetic field structures that would continue glowing for millions of years into the future. The Meerkat images showed that many filaments are grouped, 43 separate groupings containing 174 individual filaments. Some groups contain just 2 or 3 filaments, others contain 10. 15. The radio arc alone contains 17 parallel filaments, all running perpendicular to the galactic plane, all separated by an average spacing of 17 arc seconds, that is 0.2 parsecs, 2/3 of a light year, between each thread. This regular spacing is inexplicable. There is no known physical process that creates structures with such precise organization. If the filaments were expanding supernova shells, they would overlap and merge. If they were outflows from compact objects, they would diverge as they traveled away from their sources. Instead, they maintained parallel trajectories across tens of parsecs, like contrails from aircraft that never converge or spread, frozen in the sky. The discovery revolutionized our understanding of the galactic center, or rather, it destroyed our understanding, because the filaments revealed that something is happening at the core of our galaxy that operates according to principles we do not comprehend. The galactic center is not just a collection of stars and gas orbiting a supermassive black hole. It is a machine, an engine, a structure that generates magnetic fields and accelerates particles through mechanisms that remain completely mysterious 4 decades after their discovery. When you look at the Meerkat images of the galactic center filaments, your brain tries to find patterns. It tries to impose order. This is what human minds do. We see faces in clouds, constellations in random star fields, meaning in chaos. But the filaments are not random. The patterns are real, and that is what makes them so profoundly disturbing. The filaments are organized into groups, not scattered randomly through space, not distributed according to the smooth probability distributions that govern most astrophysical phenomena. They cluster, they align, they maintain precise separations that suggest some underlying organizational principle that we do not understand. Yusufzadeh and his team identified 43 distinct groupings in their statistical analysis published in 2022. These groupings contain between 2 and 17 individual filaments each. The filaments within each group run parallel to each other, maintaining constant separations across distances of tens of parsecs. This is not supposed to happen in astrophysics. Consider the physical scales involved. 1 parsec is 3.26 light-years. The distance light travels in 3.26 years. That is 30 trillion kilometers. That is 6,400 times the distance from Earth to Neptune. And the filaments maintain parallel alignments and constant separations across 20 parsecs. 30 parsecs. 40 parsecs. Over distances so vast that light takes more than a human lifetime to cross them. The radio arc provides the clearest example of this impossible geometry. 17 filaments. All parallel. All perpendicular to the galactic plane. Separated by an average of 17 arcseconds. At the distance of the galactic center, 26,000 light-years, 17 arcseconds corresponds to 2/3 of a light-year. 0.2 parsecs. Between each thread, maintained across a structure that spans dozens of light-years. Think about what this means. Imagine 17 laser beams shot from Earth toward the galactic center, perfectly parallel, separated by specific distances. Now imagine those laser beams maintaining their parallel alignment and precise spacing as they travel for tens of light-years through space. The slightest gravitational perturbation would cause them to converge or diverge. The expansion of space itself would alter their separations. Random turbulence in the interstellar medium would scatter them. Yet the filaments maintain their geometry for millions of years. Across distances that dwarf human comprehension, Yusufzadeh and his collaborators measured the spacing between filaments in multiple groupings. The radio arc has 17 arcsecond spacing. A grouping of filaments surrounding the ring-shaped H2 region G0.17 plus 0.15 shows 7 harp-like filaments with mean spacing of 16.2 arcseconds. Another grouping contains 12 filaments with spacing of 12 arcseconds. The numbers vary, but within each grouping, the spacing is remarkably constant. The filaments are not drifting. They are locked into configurations that persist across cosmic time. This is what Yusufzadeh meant when he said the filaments resembled the strings of a harp, not just because they are long and thin, but because they are organized like musical instruments, parallel strings, equally spaced, stretched across a frame. Except there is no frame, no physical structure holding them in position. They float in space, maintained by forces we do not understand. The morphology of the filaments adds another layer of mystery. Some are perfectly straight, geometric lines drawn through space with a ruler. Others curve, twist, fragment into multiple branches, create loop structures that reconnect with themselves. The Meerkat images show filaments that split at junctions, a single thread dividing into 2 prongs, like a river branching into tributaries. Except rivers branch because they encounter obstacles, because erosion carves channels, because gravity pulls water downhill. What causes a magnetic structure carrying relativistic electrons to split into 2 parallel threads? Some filaments show what researchers call cometary tail morphology, a bright head region followed by a long, fainter tail. As if something is moving through the interstellar medium, trailing a wake of synchrotron emission behind it. But these cometary structures are not moving. They are frozen, locked in place. The Meerkat observations show no evidence of motion. The filaments observed in 2022 occupy the same positions as filaments observed in the 1980s. 40 years. No measurable change. These are not dynamic phenomena. They are static structures that have remained in place for millions of years. The orientation of the filaments reveals another pattern that should not exist. Most of the originally discovered filaments run perpendicular to the galactic plane, standing vertically like pillars, towering above and below the disk. This orientation suggested that the filaments might be related to the galaxy's global magnetic field. In the disk of a spiral galaxy, magnetic fields generally run parallel to the plane, following the rotation of stars and gas. But in the halo, above and below the disk, fields can be oriented perpendicular to the plane, shaped by outflows and cosmic rays escaping from the star-forming regions below. The vertical orientation of the galactic center filaments fit this picture. They could be magnetic flux tubes anchored in the disk, buoyantly rising into the halo like smoke from a chimney. carrying cosmic rays out of the dense galactic center environment into the more tenuous halo. This would explain their vertical orientation, their long, thin morphology, their persistence over millions of years. But then Meerkat discovered the weaker filaments, and the pattern broke. Many of the fainter structures do not run perpendicular to the plane. They orient randomly, some at 45-degree angles, some almost horizontal, some twisted into complex three-dimensional curves that defy any simple geometric description. The vertical orientation is not universal, it is just one configuration among many. This destroyed the hypothesis that the filaments trace the global galactic magnetic field. If they followed the large-scale field, they would all share similar orientations. The discovery of randomly oriented filaments meant that something else was creating these structures. Something that could produce magnetic field configurations independent of the galaxy's overall field geometry. The distribution of filaments across the galactic center region adds yet another puzzle. They are not uniformly distributed. They concentrate in certain areas. The radio arc region at galactic longitude 0.2 degrees contains dozens of filaments. The region around Sagittarius C at longitude -0.5 degrees hosts another concentration. But large areas of the galactic center appear devoid of filaments. Empty zones where the conditions apparently do not support their formation. This patchy distribution suggests that the filaments require specific environmental conditions to form. Perhaps certain magnetic field strengths, perhaps specific densities of cosmic ray electrons, perhaps particular configurations of molecular clouds or H2 regions. Whatever the requirements are, they are not uniformly met across the galactic center. The filaments map out a hidden structure, an invisible architecture that determines where these threads can exist. The lengths of the filaments follow a distribution that peaks around 10 to 20 parsecs. 30 to 60 light-years. Most filaments fall in this range, but the distribution has a long tail extending to 150 light-years for the longest structures. This length distribution suggests that the filaments are created by a process with a characteristic scale, something that naturally produces structures of certain sizes. But what process operates on scales of tens of parsecs in the galactic center environment? Star formation regions are typically a few parsecs across. Supernova remnants expand to perhaps 10 parsecs before dissolving into the interstellar medium. Outflows from the central black hole might extend for hundreds of parsecs. But the filaments occupy an intermediate scale, too large to be individual stellar phenomena, too small to be galaxy-scale structures. They exist in a size range that lacks obvious physical analogs. The Meerkat team applied a technique called difference of Gaussians filtering to enhance the visibility of the filaments against the complex background emission. This mathematical process subtracts smoothed versions of the image from the original, removing large-scale structures and emphasizing fine details. When they applied this filter, hundreds of additional faint filaments emerged from the noise. Structures that were invisible in the raw data, hidden beneath the bright radio glow of the galactic center. This revealed that the filaments are even more numerous than initially suspected. The 1,000 filaments identified in the 2022 papers represent only the brightest examples. The faintest structures detected by Meerkat are still well above the telescope's noise limit, suggesting that even fainter filaments likely exist below the current detection threshold. The true population might number in the thousands, perhaps tens of thousands, pervading the entire galactic center region in a vast network of magnetic threads. The spectra of the filaments provide crucial information about the particles producing the synchrotron emission. Radio astronomers measure spectral index, the rate at which the brightness of a source changes with frequency. Thermal sources have positive spectral indices. They get brighter at higher frequencies. Non-thermal synchrotron sources have negative spectral indices. They get brighter at lower frequencies. The steepness of the spectral index reveals how rapidly the cosmic ray electrons are losing energy to synchrotron radiation. The galactic center filaments have spectral indices ranging from approximately -0.5 to -1.5. This indicates that they are definitely synchrotron sources, and that the cosmic ray electrons have a range of ages and energy distributions. The flatter spectra suggest younger electrons that have not yet radiated away significant energy. The steeper spectra indicate older electrons that have been emitting synchrotron radiation for longer periods. Interestingly, different filaments within the same grouping can have different spectral indices. The radio arc contains filaments with relatively flat spectra compared to other galactic center filaments. This suggests that the electrons in the radio arc are being continuously replenished. Something is actively injecting fresh relativistic electrons into those magnetic structures. Otherwise, they would radiate away their energy and fade from view. The polarization of the radio emission reveals the orientation of the magnetic fields threading the filaments. Synchrotron radiation is intrinsically polarized. The electric field oscillates perpendicular to the magnetic field that curves the electron's trajectory. By measuring the polarization angle, astronomers can map the magnetic field orientation along the length of each filament. The MeerKAT polarimetry data shows that the magnetic fields run parallel to the filaments along their lengths, not perpendicular to them. This means the filaments are not compression waves or shocks moving across field lines. They are the field lines themselves, made visible by the cosmic ray electrons spiraling along them. The degree of polarization varies between 10 and 40%. Lower than the theoretical maximum of 75% for perfectly ordered synchrotron emission, this depolarization indicates that the magnetic fields are not perfectly aligned. There is turbulence, tangling, small-scale disorder superimposed on the large-scale organized structure. The filaments are not pristine magnetic flux tubes. They are complex dynamic structures with internal structure that we cannot resolve with current telescopes. Rotation measure studies reveal how the magnetic field orientation changes along the line of sight through the filament. As polarized radio waves travel through magnetized plasma, their polarization angle rotates. The amount of rotation depends on the electron density, the magnetic field strength, and the path length through the plasma. By measuring rotation measures at multiple frequencies, astronomers can probe the three-dimensional magnetic field structure. The galactic center filaments show rotation measure variations that indicate a checkerboard pattern of alternating magnetic field polarities, as if the field reverses direction on small scales, creating cells of opposite polarity adjacent to each other. This suggests that the galactic center magnetic field is more complex than simple models predict. It has structure on scales of parsecs, possibly driven by turbulence in the orbital motion of gas around the central black hole. Every measurement reveals more complexity. Every new observation raises more questions. The filaments are organized, but the organization follows rules that do not match any known physical process. They are geometric, but the geometry is not Euclidean. They are stable. But the stability requires mechanisms that remain unidentified. They are the signature of something operating at the heart of our galaxy that we have not yet learned to read. The filaments glow, not in visible light, not in infrared. They emit radio waves. Specifically, they produce synchrotron radiation. And understanding what synchrotron radiation is and what it requires reveals just how impossible these structures truly are. Synchrotron radiation is light produced by charged particles moving at relativistic speeds through magnetic fields. Not just fast, relativistic, speeds approaching the speed of light. When an electron travels at 99% of light speed and encounters a magnetic field, the field curves its trajectory. The electron spirals, and as it spirals, it radiates electromagnetic energy. This is synchrotron emission. The frequency of the radiation depends on two factors: the strength of the magnetic field and the energy of the electron. Stronger fields and higher energy electrons produce higher frequency radiation. The galactic center filaments emit primarily at radio frequencies, between a few hundred megahertz and several gigahertz. This tells us that the magnetic field strengths are on the order of 10 to 100 microgauss, that is 100,000 times weaker than a refrigerator magnet. But across scales of hundreds of light years, such fields contain enormous total energy. The electrons producing this radiation must have energies in the giga-electron volt range, 1 billion electron volts. For comparison, the electrons in a television cathode ray tube have energies of perhaps 20,000 electron volts. The electrons in the galactic center filaments are 50,000 times more energetic. These are cosmic ray electrons. particles that have been accelerated to absurd velocities by some violent process. The term cosmic ray is misleading. Cosmic rays are not rays, they are particles, mostly protons, some helium nuclei, a smaller fraction of heavier elements, and electrons. They rain down on Earth constantly, millions of them per second. Most originate from supernova explosions within our galaxy. The shock waves from dying stars accelerate particles to incredible energies, launching them into interstellar space where they wander for millions of years before eventually dissipating their energy through collisions and radiation. But the cosmic ray electrons illuminating the galactic center filaments are special. They are not diffusing randomly through space, they are confined, trapped along magnetic field lines, spiraling along narrow flux tubes that stretch for dozens of parsecs. This confinement is what creates the filamentary structure. If the electrons were free to wander, they would spread out, create diffuse glows. Instead, they mark out precise one-dimensional structures, the magnetic field lines themselves. This raises the first major question. How do you confine cosmic ray electrons to such narrow paths? Magnetic field lines are not physical objects. They are mathematical constructs. Lines of force that represent the direction a magnetic field points at each location in space. In reality, magnetic fields are continuous, smoothly varying. Particles can cross field lines if turbulence or collisions scatter them. Over time, cosmic ray electrons should diffuse perpendicular to field lines, spreading out, erasing any initial filamentary structure. The fact that the galactic center filaments remain so sharply defined after millions of years suggests that the magnetic fields are somehow special. They must be much stronger than the surrounding field, creating magnetic flux tubes, bundles of field lines that are effectively isolated from the weaker fields around them. Think of them as magnetic highways. Cosmic rays can travel freely along the tube, but crossing out of the tube requires overcoming a magnetic pressure gradient. The strong field inside resists the intrusion of the weaker field outside. This allows the flux tube to maintain its identity, to persist as a distinct structure embedded in the larger magnetic environment. But this explanation immediately creates another problem. How do you create magnetic flux tubes in the first place? And how do you maintain them for millions of years against the turbulent, chaotic environment of the galactic center? Magnetic fields in astrophysics do not spring into existence spontaneously. They are generated by electric currents, by the motion of charged particles. In the disks of galaxies, differential rotation creates large-scale magnetic fields through a process called the dynamo effect. As the inner parts of the disk rotate faster than the outer parts, magnetic field lines get wound up, stretched, amplified. This creates the organized spiral magnetic fields observed in galaxies like the Milky Way. But the galactic center is not a simple rotating disk. It is a maelstrom. Gas orbits at hundreds of kilometers per second. Supernova shockwaves blast through the interstellar medium at thousands of kilometers per second. Massive stars pump enormous quantities of energy into their surroundings through stellar winds. The supermassive black hole occasionally erupts, driving outflows that clear out vast bubbles of space. In this environment, magnetic fields should be tangled, chaotic, not organized into pristine flux tubes maintaining parallel alignments for millions of years. The equipartition magnetic field strength can be calculated from the observed synchrotron emission. This is the field strength at which the energy density in the magnetic field equals the energy density in the cosmic ray particles. It represents a kind of equilibrium state. Neither the field nor the particles dominate. For the galactic center filaments, equipartition calculations give field strengths ranging from tens to hundreds of microgauss, with typical values around 100 microgauss. That is 10,000 times stronger than the average interstellar magnetic field in the galactic disk. These are not weak fields. 100 microgauss sustained over a volume 10 parsecs long and 0.1 parsecs wide contains magnetic energy equivalent to 10,000 supernovae. That is an almost incomprehensible amount of energy. And it is somehow organized into thread-like structures rather than dispersed throughout the galactic center. The polarization measurements reveal that the magnetic field is coherent along the entire length of each filament. The polarization angle changes slowly and smoothly, not randomly. This indicates that the field maintains a consistent orientation across tens of light years. Again, this should not happen in a turbulent environment. Turbulence creates tangled fields, regions where the field direction changes on small scales. The coherent fields in the filaments suggest that they are somehow protected from turbulence, isolated in structures that resist disruption. Some researchers have proposed that the filaments are magnetic Rayleigh-Taylor instabilities. These occur when a lighter fluid tries to support a heavier fluid against gravity. The interface becomes unstable, ripples grow. Eventually, fingers of the heavy fluid penetrate downward while bubbles of the light fluid rise upward. In the galactic center, cosmic ray pressure might create a similar instability. Cosmic rays are relativistic particles. Their pressure can exceed the thermal pressure of ordinary gas. If cosmic rays accumulate in a layer, they might drive instabilities that create finger-like structures. The filaments could be the visible manifestation of these instabilities. Cosmic rays flowing along magnetic flux tubes that have been shaped by magnetohydrodynamic instabilities. But Rayleigh-Taylor instabilities typically create structures with sizes comparable to the wavelength of the fastest-growing mode. For the galactic center, this should be a few parsecs, not 100 parsecs. The longest filaments are far too long to be explained by simple instability theory. Something else must be stretching them, maintaining their structure across scales that exceed the characteristic size of the instability. Other theories propose that the filaments are cosmic string candidates. In the early universe, during phase transitions in the first fraction of a second after the Big Bang, topological defects might have formed. One-dimensional defects called cosmic strings. These would be incredibly thin, smaller than an atomic nucleus in diameter, but incredibly massive, stretching energy across cosmic distances. If cosmic strings exist, and if one happened to pass through our galaxy, it might accumulate magnetic fields and cosmic rays along its length, creating a filamentary structure that persists indefinitely. This theory was popular in the late 1980s. It explained the thinness of the filaments, the extreme magnetic field strengths, the stability over cosmic time. Cosmic strings would not diffuse or dissipate. They are topological defects in space-time itself. But the theory faced serious problems. Cosmic strings should oscillate, vibrating like plucked guitar strings at relativistic speeds. The galactic center filaments show no evidence of motion. They are static. Additionally, some filaments appear to split or merge. Cosmic strings cannot split. They are fundamental objects with no internal structure. The discovery of branching filaments ruled out the cosmic string hypothesis. The most widely accepted explanation today involves magnetic flux tubes generated by the complex interaction of multiple astrophysical processes. Star formation in the central molecular zone creates massive stars. These stars have powerful stellar winds. When they die in supernova explosions, they pump energy and magnetic fields into their surroundings. The expanding supernova remnants compress the interstellar magnetic field, amplifying it, creating regions of strong field embedded in the weaker background. Simultaneously, the central supermassive black hole drives outflows. Sagittarius A star is not currently accreting large amounts of matter. It is relatively quiet compared to the supermassive black holes in active galaxies. But it was not always quiet. Evidence suggests that a few million years ago, Sagittarius A star underwent a major outburst, possibly triggered by the tidal disruption of a star that wandered too close, or by the infall of a giant molecular cloud. During this outburst, the black hole would have driven powerful winds, bipolar outflows streaming away from the accretion disk at thousands of kilometers per second. These outflows interact with the surrounding medium. They shock heat gas, they compress magnetic fields, they accelerate cosmic rays. The filaments might form where these various processes intersect, where a supernova remnant's expanding shell encounters the outflow from Sagittarius A star, where stellar winds collide with molecular clouds, where cosmic rays accelerated by one source flow along magnetic fields shaped by another. The galactic center is an environment of violent interactions, and the filaments are the visible scars, the places where these interactions have organized magnetic fields and cosmic rays into thread-like structures that glow in radio waves. But even this complex multi-process explanation struggles to account for the observed properties. The extreme lengths, the precise parallel alignments, the persistence over millions of years. Every theory can explain some features. None can explain all of them. The filaments remain fundamentally mysterious. The synchrotron emission itself imposes strict requirements on the particles and fields. The cosmic ray electrons lose energy rapidly through synchrotron radiation. An electron with an energy of 1 giga-electron-volt moving through a 100 microgauss field radiates away half its energy in approximately 1 million years. After 10 million years, the electron's energy has decreased by a factor of 1,000. It no longer produces detectable radio emission at the frequencies Meerkat observes. This means the electrons must be continuously replenished. Something must be actively injecting fresh cosmic rays into the filaments. Otherwise, they would fade from view within a few million years. The fact that we see filaments that appear 6 million years old suggests that the injection process has been operating for at least that long. Possibly much longer if the filaments are older than the electrons currently illuminating them. What could sustain cosmic ray injection for millions of years? Individual supernova explosions are brief events. They last for decades, perhaps a century as the shockwave expands and accelerates particles. Then the remnant fades. Stellar winds from massive stars are more persistent. A massive star lives for a few million years. Throughout its life, it pumps energy into its surroundings. But massive stars are rare, and they are distributed randomly through the central molecular zone. They cannot explain filaments that stretch for tens of parsecs through regions containing many stars. The supermassive black hole offers a more compelling source. Sagittarius A star has been active in the relatively recent past. The radio bubbles discovered by Meerkat in 2019 provide direct evidence. These bubbles extend for 1,400 light-years above and below the galactic plane. They contain hot X-ray emitting gas. And they show radiosynchrotron emission, indicating the presence of cosmic rays. The energy required to inflate these bubbles is approximately 10 to the 56 ergs. That is 100,000 times the energy released by a supernova. Only the central black hole can produce such an enormous energy output. If Sagittarius A star drove this outburst a few million years ago, it would have accelerated enormous quantities of cosmic rays. These particles would stream outward from the black hole along magnetic field lines. Some would escape into the halo, creating the radio bubbles. Others would be trapped, confined to magnetic flux tubes in the central molecular zone, continuously spiraling along field lines, radiating synchrotron emission, creating the filaments we observe today. This picture is appealing. It connects the filaments to a known energetic event. It explains the ages. It accounts for the large number of structures. If the black hole's outburst injected cosmic rays throughout a large volume of the galactic center, hundreds or thousands of magnetic flux tubes might have been illuminated simultaneously, creating the population of filaments we observe. But it does not explain the geometry. Why are the filaments so precisely organized? Why do they maintain parallel alignments? Why are they distributed in clusters with regular spacing? The black hole's outburst would have been more or less spherically symmetric. It might have preferred directions along the rotation axis of the accretion disk, but it should not create the harp-like structures with their strings equally spaced and perfectly parallel. The synchrotron emission tells us what the filaments are made of: magnetic fields and cosmic rays. But it does not tell us how they formed, or why they exist in such impossible configurations. The light reveals the structure, but it conceals the mechanism. For 39 years, Farhad Yousafzadeh lived with one image of the galactic center burned into his mind: vertical filaments, standing perpendicular to the galactic plane, towering like monuments through space. He had discovered them in 1984. He had spent 4 decades studying them, mapping them, measuring them, trying to understand them. He knew their properties better than anyone alive: their spectral indices, their magnetic field strengths, their polarization characteristics. They had become familiar, predictable in their unpredictability. Then, in 2023, he discovered that everything he thought he knew was incomplete. The Meerkat data contained a second population of filaments, not vertical. Horizontal, running parallel to the galactic plane rather than perpendicular to it. Shorter than their vertical cousins, 5 to 10 light-years long instead of 150. But otherwise similar. One-dimensional structures. Magnetized. Emitting synchrotron radiation. Glowing in radio waves. Yusuf Zada published the discovery in the Astrophysical Journal Letters in June 2023. The paper carried a title that barely concealed his astonishment. The population of the galactic center filaments' position angle distribution reveals a degree-scale collimated outflow from SGRA along the galactic plane. The language was formal, scientific, but the implications were staggering. These horizontal filaments were not randomly oriented, they pointed, like arrows, directly at Sagittarius A star. In interviews, Yusuf Zada was more candid about his reaction. "I was actually stunned when I saw these," he said. "We had to do a lot of work to establish that we weren't fooling ourselves." After decades of studying vertical filaments, the existence of a horizontal population had never occurred to him. "We have always been thinking about vertical filaments and their origin," he explained. "I'm used to them being vertical. I never considered there might be others along the plane." The discovery required statistical analysis to confirm. Individual horizontal filaments had been visible in the MeerKAT images all along, but they look similar to other structures in the galactic center. Thermal filaments associated with star-forming regions. Ionized gas around hot stars. Without careful analysis, the non-thermal horizontal filaments were indistinguishable from thermal features that have completely different origins. Yusuf Zada and his collaborators used filtering techniques to isolate the synchrotron-emitting structures from the thermal background. They measured position angles, the orientation of each filament on the sky, then they plotted the distribution. And the pattern emerged. Clear, undeniable. Hundreds of short filaments concentrated at negative galactic longitudes, almost all oriented within plus or minus 20 degrees of the galactic plane. And when you extended their position angles backward, when you traced the lines they defined through space, they converged, all pointing toward the same location. Galactic coordinates longitude 0, latitude 0. The position of Sagittarius A star. This radial distribution was unprecedented. The vertical filaments showed no preferred orientation. They scattered randomly around perpendicular to the plane. Some tilted slightly north, others slightly south. But on average, they stood vertical with no systematic pattern. The horizontal filaments were completely different. They were organized, aligned, pointing at the central black hole like spokes on a wheel. Like tentacles reaching toward a central hub, like fingers grasping at the singularity lurking at the galaxy's heart. The morphology of the horizontal filaments differed from the vertical population in other ways as well. They were shorter, 5 to 10 light-years instead of 50 to 150. They appeared in less organized groups, not the harp-like arrangements of equally spaced parallel strings. Instead, they scattered more irregularly. Some isolated, some in small clusters of 2 or 3. They looked, in Yusuf Zada's words, like the dots and dashes of Morse code. Short segments, punctuating the galactic plane on one side of Sagittarius A star. This asymmetry was striking. The horizontal filaments concentrated on the negative longitude side of the galactic center, west of the black hole if you imagine looking at the galactic center from Earth. The positive longitude side, east of the black hole, showed far fewer horizontal structures. This lopsidedness suggested that the mechanism creating the horizontal filaments was directional, not a spherically symmetric process, something emanating preferentially in one direction along the galactic plane. The spectral properties of the horizontal filaments revealed even more differences from the vertical population. While some horizontal filaments emitted non-thermal synchrotron radiation identical to the vertical threads, others showed evidence of thermal emission. Radiation from hot gas rather than relativistic particles. This suggested that the horizontal population was actually two distinct types of structures. Some true non-thermal filaments, similar to the vertical population. Others thermal features that happened to be aligned radially toward Sagittarius A star. Yusuf Zeta proposed that the two types of horizontal filaments formed through different mechanisms. The non-thermal horizontal filaments, he suggested, were originally vertical filaments that had been snipped and reoriented by an outflow from the central black hole. Imagine a powerful wind streaming outward from Sagittarius A star along the galactic plane. This wind encounters a vertical filament. The collision distorts the magnetic structure, breaks it. The fragment gets caught in the outflow, dragged along, rotated to point back toward its source. The vertical thread becomes a horizontal spoke, still emitting synchrotron radiation, but now aligned with the outflow direction. The thermal horizontal filaments formed through a different process. Sagittarius A star's outflow encounters regions of ionized gas, H2 regions, clouds of hydrogen plasma surrounding hot massive stars. The outflow compresses these regions, stretches them, creates elongated structures aligned with the flow direction. These thermal filaments are not cosmic ray and magnetic field structures. They are dense ionized gas shaped by hydrodynamic pressure, but they appear as filamentary structures in radio images, mimicking the non-thermal population. This dual origin explained the mixed properties, why some horizontal filaments showed non-thermal spectra and others thermal, why some were strongly polarized indicating organized magnetic fields while others were unpolarized indicating turbulent thermal emission. The horizontal population was not a single phenomenon. It was two separate types of structures, both created by the same underlying cause, an outflow from Sagittarius A star along the galactic plane. The age of the horizontal filaments provided crucial evidence for this interpretation. Yusuf Zeta estimated they were approximately 6 million years old, the same age as many of the vertical filaments. This temporal coincidence was not accidental. It suggested that both populations formed during the same event, the explosive outburst from Sagittarius A star that occurred a few million years ago. The same event that inflated the giant radio bubbles extending above and below the galactic plane. But while the radio bubbles showed the vertical extent of the outburst, the horizontal filaments revealed something new. The outflow had not been purely bipolar, not just directed perpendicular to the galactic plane. It also had a component along the plane. A lateral flow, streaming outward in the disk, colliding with vertical filaments in H2 regions, shaping them, reorienting them, creating the spoke-like pattern of horizontal structures pointing back toward the black hole. This discovery revolutionized understanding of how Sagittarius A star interacts with its surroundings. Previous models assumed that outflows from supermassive black holes were primarily perpendicular to the accretion disk. Bipolar jets, driven along the rotation axis. The vertical radio bubbles fit this picture perfectly, but the horizontal filaments indicated that the outflow was more complex, three-dimensional, with components both perpendicular and parallel to the disk. The orientation of the horizontal filaments also revealed information about the black hole's accretion disk geometry. If the outflow responsible for creating the horizontal filaments lies along the galactic plane, then the accretion disk around Sagittarius A star must also lie approximately in the galactic plane. The disk's rotation axis is perpendicular to the plane. This alignment makes sense. The black hole accretes material from the surrounding molecular clouds. These clouds orbit in the galactic disk. Material falling onto the black hole naturally forms an accretion disk aligned with the galactic plane. But this raises a puzzle. If the accretion disk lies in the galactic plane, then bipolar outflows should be perpendicular to the plane, which they are. The radio bubbles extend vertically. But the horizontal filaments suggest an additional outflow component in the plane. How can a black hole produce both vertical and horizontal outflows simultaneously? Yusuf Zeta suggested that the horizontal outflow might not come directly from the black hole. Instead, it could result from the vertical outflow impacting the dense molecular gas in the central molecular zone. The vertical outflow streams away from the black hole. It hits the disk. The collision creates a shock. The shocked gas flows laterally, spreading outward along the plane, like water hitting a tabletop and spreading in all directions. This lateral flow is the horizontal outflow, not driven directly by the black hole, but a secondary consequence of the vertical outflow interacting with the surrounding environment. This model explains several features. The asymmetry of the horizontal filaments. If the vertical outflow hits the disk at a slight angle, or if the disk density is asymmetric, the lateral flow will be stronger in some directions than others. The concentration of horizontal filaments on one side of Sagittarius A star suggests that conditions on that side favor the creation or preservation of these structures. The model also explained why horizontal filaments are shorter than vertical ones. The vertical filaments form in the lower density halo environment. Cosmic rays and magnetic fields can extend for large distances without being disrupted. The horizontal filaments form in the denser disk. Where collisions with molecular clouds and interactions with stellar winds limit their extent, the environment constrains their growth, keeping them short. Fragmentary. The discovery of the horizontal filaments demonstrated that the galactic center's structure was far more complex than previously imagined. Not just vertical magnetic flux tubes, but a three-dimensional network of magnetic structures shaped by multiple outflow components. Vertical flows driven by the black hole's rotation axis. Horizontal flows created by the interaction of vertical flows with the disk. All of this overlaid on the chaotic background of supernova remnants, stellar winds, and molecular cloud dynamics. Ian Haywood, who collaborated on the discovery, emphasized the importance of MeerKAT's unique capabilities. The telescope's sensitivity allowed detection of structures that had been invisible to previous instruments. Its resolution revealed morphological details that distinguished horizontal filaments from other features. And the quality of the data enabled statistical analysis that demonstrated the radial orientation pattern. Without MeerKAT, the horizontal filaments would have remained hidden, another population of structures lurking in the data, waiting for someone to notice them. The existence of two distinct filament populations with different orientations, different lengths, and different formation mechanisms suggested that the galactic center was capable of producing an even greater diversity of structures than anyone had suspected. If vertical and horizontal filaments existed, what other populations remained undiscovered? Were there intermediate orientations? Curved structures connecting the vertical and horizontal populations? Three-dimensional networks invisible in two-dimensional projected images? Yousafzadeh acknowledged that much work remained. "Our work is never complete," he said. "We always need to make new observations and continually challenge our ideas and tighten up our analysis." The horizontal filaments opened new questions, even as they provided potential answers to old ones. They demonstrated that the galactic center harbored more secrets than 4 decades of observation had revealed, that improved instruments did not just refine existing knowledge. They discovered entirely new phenomena hiding beneath the noise floor of previous generations of telescopes. The connection between the horizontal filaments and Sagittarius A star's outflow provided the first direct link between the filaments and the central black hole. For decades, the vertical filaments had floated in observational limbo, clearly associated with the galactic center, but not obviously connected to any specific source. The horizontal filaments changed this. Their radial orientation pointed directly at the black hole. Their ages matched the timing of the black hole's recent outburst. The evidence was circumstantial, but it was compelling. The black hole was not just a passive gravitational anchor. It was actively shaping the magnetic structure of the galactic center, creating the conditions that allowed filaments to form. This realization transformed how astronomers thought about supermassive black holes in general, not just in the Milky Way, but in all galaxies. If Sagittarius A star could create filamentary structures through its outflows, then other supermassive black holes should do the same. And indeed, subsequent observations with MeerKAT and other radio telescopes revealed filamentary structures in the centers of other galaxies. Similar geometries, similar radio properties. The galactic center filaments were not unique to the Milky Way. They were a generic feature of galactic nuclei, created whenever conditions allowed supermassive black holes to drive powerful outflows into magnetized environments. But the discovery of the horizontal filaments also highlighted how much remained unknown. If the black hole's outflow could reorient and fragment vertical filaments to create horizontal ones, what else might it be doing? Were there even shorter fragments too faint for MeerKAT to detect? Were there transitional structures caught in the act of being rotated from vertical to horizontal? And most importantly, what created the vertical filaments in the first place? The horizontal population could be explained as byproducts of interactions with the vertical population. But the vertical structures themselves still lacked a complete explanation. They remain the fundamental mystery, the original enigma that had haunted Yusuf Zeta for nearly 40 years. Magnetic fields are invisible. You cannot see them. You cannot touch them. They pass through your body right now without resistance. Earth's magnetic field extends thousands of kilometers into space, wrapping our planet in a protective cocoon that deflects the solar wind. You do not feel it. The only reason we know it exists is because it makes compass needles point north, and because astronauts orbiting above the atmosphere would be killed by radiation without its shielding. In the galactic center, magnetic fields are not invisible. The cosmic ray electrons spiraling along field lines make them glow. Each filament is a magnetic field line rendered visible through synchrotron emission. What we see when we look at the MeerKAT images is not the matter, not the gas or dust or stars. We are seeing the magnetic field itself, the fundamental structure of space as it curves and twists through the galaxy's core. The magnetic field strength in the filaments can be calculated from the synchrotron emission. This calculation relies on the principle of equipartition, the assumption that magnetic energy and cosmic ray particle energy are roughly equal. Neither dominates. They exist in a kind of balance. For the galactic center filaments, this gives field strengths between 50 and 200 microgauss, with most filaments clustered around 100 microgauss. 100 microgauss is 1/1,000,000th of a Gauss, 1/10,000th of Earth's surface magnetic field. It sounds weak, but spread across volumes tens of parsecs on a side, containing trillions of cubic kilometers, the total magnetic energy becomes enormous. A single filament 100 light-years long contains magnetic energy equivalent to the total rest mass energy of 10,000 suns, not the fusion energy they produce over their lifetimes. The rest mass energy, E equals mc squared. The energy released if you could convert 10,000 solar masses directly into pure energy. This energy is not uniformly distributed. The filaments are bright. The regions between them are dark. This means the magnetic field is concentrated into narrow flux tubes, bundles of field lines that are magnetically isolated from their surroundings. The field strength inside the tubes is 100 microgauss. Outside, in the ambient interstellar medium, the field is perhaps 10 microgauss. A factor of 10 weaker. This pressure difference is what maintains the filament structure. The strong field inside resists compression from outside. The weak field outside cannot penetrate the flux tube. The boundary remains stable. But this stability is puzzling. Magnetic flux tubes and laboratory plasmas are notoriously unstable. They develop kink instabilities, sausage instabilities, ballooning instabilities. The tubes twist and contort and eventually disrupt, breaking into smaller fragments, or expanding and dissolving into the background field. The fact that galactic center filaments maintain their coherence for millions of years suggests that they are somehow stabilized against these instabilities. One possibility is that the filaments are not isolated flux tubes at all. They might be density enhancements within a larger-scale magnetic structure, like the bright regions in fluorescent light tubes. The tube contains low-pressure gas and a uniform electric field, but the glow concentrates in filamentary streamers, regions where ionization is enhanced, creating visible structures within a uniform background. Perhaps the galactic center magnetic field is similar. Large-scale organized field pervading the entire central molecular zone, and the filaments are regions where cosmic ray density is enhanced, making the field visible without requiring it to be topologically distinct from its surroundings. This model avoids the stability problem. If the filament is just a brighter region within a continuous field, it does not need to resist instabilities. There are no flux tube boundaries to disrupt. The cosmic ray density can vary smoothly, creating bright filaments where particle density is high and dark regions where it is low. The magnetic field remains continuous throughout. But this model cannot explain the sharpness of the filaments. The MeerKAT images show edges, boundaries where the emission drops rapidly, not smooth gradients. If the filaments were just cosmic ray density enhancements in a uniform field, we would expect them to fade gradually. Instead, they appear as discrete structures, suggesting that the magnetic field really is organized into distinct flux tubes. The polarization measurements provide additional evidence for the flux tube interpretation. The radio emission from the filaments is linearly polarized, meaning the electric field oscillates in a preferred direction. For synchrotron radiation, this polarization direction is perpendicular to the magnetic field. By measuring the polarization angle across a filament, astronomers can map how the field orientation changes. The results show that the magnetic field runs along the length of the filaments, parallel to their long axis, and the field direction remains coherent across the entire structure, not randomly oriented, not tangled, but smoothly varying, maintaining a consistent orientation across tens of parsecs. This coherence is the signature of a true magnetic flux tube, a bundle of field lines that share a common topology, isolated from the surrounding field. The rotation measure maps reveal even more structure. As polarized radio waves travel through magnetized plasma, their polarization angle rotates. The amount of rotation depends on the electron density, the magnetic field strength parallel to the line of sight, and the distance the light travels through the plasma. By measuring how much the polarization angle changes with wavelength, astronomers can calculate the rotation measure. This quantity probes the magnetic field structure along the line of sight, revealing field components we cannot see in the projected images on the sky. The galactic center filaments show rotation measure values ranging from hundreds to thousands of radians per meter squared. These are enormous values. For comparison, rotation measures through the general interstellar medium are typically just a few tens of radians per meter squared. The large rotation measures in the galactic center indicate either very strong magnetic fields, very high electron densities, or very long path lengths through the magnetized plasma. Probably all three. But the spatial distribution of rotation measure is more interesting than the absolute values. The rotation measure varies systematically across the galactic center in a checkerboard pattern. Regions of positive rotation measure adjacent to regions of negative rotation measure. This pattern indicates that the magnetic field changes direction on relatively small scales, perhaps a few parsecs, creating cells of alternating field polarity. This checkerboard pattern might result from the orbital motion of gas in the galactic center. As molecular clouds orbit Sagittarius A star, they drag magnetic field lines with them. The shearing motion between clouds on different orbits twists the field, creating alternating regions where the field points toward us and away from us. Like the surface of a rope made from twisted fibers. Viewed end-on, you see alternating fibers oriented in opposite directions. The magnetic field structure in the galactic center is therefore not simple. It is not a uniform field pervading the entire region, nor is it a collection of completely independent flux tubes. Instead, it appears to be a hierarchical structure. A large-scale field shaped by the rotation of gas around the central black hole. Embedded within this large-scale field are intermediate-scale structures, perhaps loops or sheets created by supernova explosions and stellar winds. And embedded within these intermediate structures are the small-scale flux tubes, the filaments themselves. Bright threads where cosmic rays are concentrated and where the field strength is amplified. The amplification mechanism remains unclear. How do you take a 10 microgauss ambient field and compress it into a 100 microgauss flux tube without the structure immediately dispersing? One possibility is dynamic compression. If a supernova shockwave sweeps through the interstellar medium, it compresses the magnetic field ahead of it. The compressed field can reach strengths 10 times higher than the ambient field. If cosmic rays are accelerated at the shock front, they get injected into this amplified field region, creating a filament. But supernova shocks are spherical. They expand in all directions. The compressed field ahead of a shock forms a shell, not a filament. To create a one-dimensional structure, you need an asymmetry. Perhaps the shock encounters a pre-existing density gradient, or a pre-existing magnetic field structure. The interaction between the spherical shock and the asymmetric environment might create elongated compressed regions, filamentary structures that persist after the shock has passed. Another possibility is magnetic reconnection. When oppositely directed magnetic field lines encounter each other, they can reconnect, snap together, and rearrange themselves into lower energy configurations. This process converts magnetic energy into kinetic energy, accelerating particles to high velocities. And it can create elongated current sheets, thin regions where the reconnection is occurring. These current sheets might be visible as radiofilaments, especially if the reconnection is ongoing. Continuously injecting fresh relativistic particles into the structure, theoretical models of magnetic reconnection in the galactic center environment suggest it could operate efficiently. The tangled magnetic fields, the high electron densities, the turbulent gas motions, all of these factors enhance the reconnection rate. But reconnection typically creates sheet-like structures, not thread-like filaments. And reconnection events are transient. They last for years or decades, not millions of years. The persistence of the filaments argues against reconnection as the primary mechanism. The most comprehensive theory involves cosmic ray-driven instabilities. Cosmic rays are not just passively following magnetic field lines. They actively shape the field structure. When cosmic rays accumulate in a region, their pressure can exceed the thermal pressure of ordinary gas. This pressure drives instabilities. The Parker instability is one example. Named after physicist Eugene Parker, this instability occurs when cosmic ray pressure causes magnetic field lines to buckle upward. Rising buoyantly like hot air balloons, the rising field lines drag gas with them, creating underdense chimneys that allow even more cosmic rays to escape. The process is self-reinforcing. In the galactic center, cosmic rays are continuously generated by supernova explosions and by acceleration in the environment around Sagittarius A star. These particles try to escape, moving along magnetic field lines, seeking regions of lower pressure. As they flow, they can amplify magnetic field structures through streaming instabilities. These instabilities occur when cosmic rays move faster than the alpha wave speed, the speed at which magnetic disturbances propagate through magnetized plasma. When cosmic rays stream faster than alpha waves, they generate waves through a resonant interaction. The waves scatter the cosmic rays, slowing them down. But the wave energy comes from the cosmic ray kinetic energy. The magnetic field grows. The amplified field then confines the cosmic rays more effectively, creating a positive feedback loop. The field grows until the cosmic rays can no longer stream faster than the alpha speed. At that point, equilibrium is reached. This process can create filamentary structures naturally. The cosmic rays flow along pre-existing field lines. The streaming instability amplifies the field along these lines. The amplification is strongest where the cosmic ray flux is highest, creating bright filaments embedded in a weaker ambient field. The filaments persist as long as the cosmic ray flux remains high, which, in the galactic center environment with its continuous sources of particle acceleration, could be millions of years. Numerical simulations of cosmic ray-driven outflows from galactic nuclei produce structures that resemble the observed filaments: long, thin, aligned with the magnetic field, exhibiting synchrotron emission from the cosmic ray electrons. The simulations cannot reproduce all the observed properties: the precise spacing between filaments, the extreme lengths of the longest structures. But they demonstrate that cosmic ray-driven processes can create filamentary structures without requiring fine-tuned initial conditions. The magnetic field in the filaments is strong enough to confine cosmic rays up to energies of approximately 10 to the 14 electron volts. That is 100 trillion electron volts. These are not the highest energy cosmic rays. Ultra-high energy cosmic rays, with energies exceeding 10 to the 18 electron volts, exist. But those particles cannot be confined by galactic magnetic fields. They escape into intergalactic space almost immediately after acceleration. The cosmic rays trapped in the galactic center filaments are intermediate energy particles, energetic enough to produce copious synchrotron radiation, but not so energetic that they escape confinement. This energy range is significant. It corresponds to the Ni in the cosmic ray spectrum, the energy at which the cosmic ray flux begins to decrease more rapidly with increasing energy. Below the Ni, Cosmic rays are believed to be primarily galactic in origin, accelerated by supernova remnants and other galactic sources. Above the knee, the origin becomes less clear, possibly extragalactic sources. The galactic center filaments provide direct evidence that galactic sources can accelerate cosmic rays to energies approaching the knee, though whether they can exceed it remains uncertain. The total cosmic ray energy contained in all the filaments is difficult to estimate precisely, but rough calculations suggest it is approximately 10 to the 50 ergs. That is 10,000 times the total energy humans have generated throughout all of recorded history, contained in invisible particles spiraling through magnetic fields at the center of our galaxy. This energy reservoir affects the galactic center environment in subtle ways. Cosmic ray pressure contributes to the vertical hydrostatic support of gas in the central molecular zone. It may suppress star formation by heating molecular clouds, and it drives outflows that transport energy away from the galactic center into the surrounding halo. The filaments are therefore not just passive tracers of the magnetic field, they are active participants in galactic center dynamics. They store energy, they transport momentum. They shape the thermal structure of the interstellar medium. Understanding their properties is essential for understanding how the galactic center operates as a system, how energy flows from sources like supernova explosions and the central black hole to the larger scales of the galactic halo, how magnetic fields mediate these energy flows, how cosmic rays propagate through magnetized plasmas. Every measurement of the filaments reveals more complexity. Every new observation raises more questions. The magnetic field is not a simple dipole, not a uniform background. It is a tangled web of structures spanning all scales. From the parsec scale flux tubes visible as filaments to the 100-parsec scale field shaped by the galactic rotation to the kiloparsec scale field extending into the halo. All of these structures interact, influence each other, create emergent behavior that cannot be predicted from studying any single scale in isolation. We are seeing the magnetic skeleton of the galactic center, the framework upon which everything else is built. Stars form in molecular clouds whose collapse is regulated by magnetic fields. Supernova remnants expand into magnetized media that constrain their evolution. Cosmic rays propagate along field lines that determine where they can travel. The black hole's outflow follows magnetic channels that focus and direct the flow. The filaments make this invisible architecture visible. They are the only structures that reveal the magnetic field directly. Without them, we would be blind to one of the most important components of the galactic center environment. Sagittarius A star is quiet now, almost silent. The 4 million solar mass black hole lurking at the exact center of our galaxy accretes material at a trickle, perhaps 1/10,000th of a solar mass per year. That is roughly the mass of Earth falling into the singularity annually. Spread over the event horizon of a supermassive black hole, this accretion rate barely registers. The black hole is starving. We know this because we can see Sagittarius A star directly. Not as an optical point of light, black holes do not emit light, but as a radio source. As material spirals inward toward the event horizon, it heats to millions of degrees. The superheated plasma radiates across the electromagnetic spectrum. X-rays, infrared, radio waves. The radio emission from Sagittarius A star has been monitored continuously for decades. A very large array, the submillimeter array, the Event Horizon Telescope, all watching the heart of our galaxy, measuring its brightness, its variability, its structure. The Event Horizon Telescope achieved something remarkable in 2022. It imaged the shadow of Sagittarius A star, not the black hole itself. You cannot see a black hole. It is a region where light cannot escape. But you can see the shadow it casts against the background glow of infalling material. The Event Horizon Telescope combined radio dishes across the entire Earth, creating an interferometer with a baseline equal to the planet's diameter. This gave it angular resolution measured in micro-arc seconds, sufficient to resolve structures at the scale of the event horizon itself. The image showed a bright ring, approximately 60 micro-arc seconds across. That is 60 millionths of an arc second. The angular size of a grapefruit on the moon as seen from Earth. Inside the ring, darkness. The shadow of the event horizon. Material orbiting just outside the last stable orbit. Heated to billions of degrees. Glowing brilliantly. Then falling past the point of no return and vanishing from our universe. The current accretion rate is pathetic. The Event Horizon Telescope observations, combined with X-ray monitoring from Chandra and other satellites, indicate that Sagittarius A star is accreting at perhaps 1/1,000,000th of the Eddington rate. The Eddington rate is the maximum luminosity a compact object can sustain through steady accretion. Above this limit, radiation pressure becomes so intense that it blows away the infalling material. Black holes accreting at the Eddington rate shine with luminosities equivalent to billions of suns. Sagittarius A star is barely glowing, a dying ember. But it was not always this way. The evidence for past activity surrounds us. The giant radio bubbles discovered by Meerkat in 2019 extend for 1,400 light-years perpendicular to the galactic plane. These are not ancient structures. Radio emission from relativistic particles fades over time as the particles lose energy. The fact that the bubbles are still visible means they are young, cosmologically speaking. The best estimates suggest they formed between 2 and 6 million years ago. The energy required to inflate these bubbles is staggering, approximately 10 to the 56 ergs. That is 1 followed by 56 zeros. To put this in human terms, it equals the total energy output of our Sun over 1 billion years, released in a few million years. Possibly much less. If the outburst that created the bubbles was particularly violent, it might have lasted only a few 100,000 years. A geological eye blink. A cosmic instant. Where did this energy come from? Only one source in the galactic center can produce such power. Sagittarius A star. During the outburst, the black hole must have been accreting at rates millions of times higher than today, perhaps approaching the Eddington limit. Material would have been falling in at tens or hundreds of Earth masses per year, spiraling through the accretion disk, heating, radiating, converting gravitational potential energy into electromagnetic radiation and kinetic energy in outflows. When material falls onto a black hole, not all of it crosses the event horizon. Some gets ejected, driven outward by magnetic fields threading the accretion disk. These outflows can be bipolar jets, narrow beams of plasma and radiation streaming away from the black hole's poles at relativistic speeds. Or they can be wider-angle winds, material blown off the inner accretion disk by radiation pressure and magnetic forces. For Sagittarius A star, the evidence suggests a wind rather than a jet, a relatively wide-angle outflow that carved out the radio bubbles we observe today. The X-ray observations provide additional evidence for past activity. The X-ray telescope Chandra has been monitoring the galactic center for over 2 decades. It detects X-ray echoes, light echoes, not from visible light, from X-rays. Molecular clouds near Sagittarius A star show X-ray emission that is not their own. They are reflecting X-rays that were emitted by some source in the past. The time delay between the original emission and the reflected echo depends on the geometry, the distance from the source to the cloud to the observer. By mapping these X-ray echoes, astronomers can reconstruct the history of X-ray emission from Sagittarius A star. The results indicate that approximately 100 to 300 years ago, the black hole brightened by a factor of 1,000,000. For a brief period, it shone as brightly as an active galactic nucleus. Then it faded, returning to its current quiescent state. This recent flare was much smaller than the outburst that created the radio bubbles. But it demonstrates that Sagittarius A star undergoes episodic increases in activity. What triggers these outbursts? The most likely explanation is the infall of material. Sagittarius A star sits in the central molecular zone, a region containing tens of millions of solar masses of molecular gas. This gas orbits the black hole at distances of a few parsecs. Most of it is stable, orbiting indefinitely without falling in. But occasionally, something disturbs the gas. A supernova shockwave, a collision between molecular clouds, the tidal disruption of a star that wandered too close to the black hole. These perturbations can send material spiraling inward. When a large quantity of gas falls towards Sagittarius A star, the accretion rate increases dramatically. The accretion disk brightens, heats, And if the infall rate exceeds what the disk can process smoothly, instabilities develop. The disk becomes turbulent. Magnetic fields amplify through dynamo processes. The increased magnetic pressure drives winds. Material gets ejected, carrying energy and momentum away from the black hole, clearing out the surrounding environment. This is not a gentle process. The outflow driven by a super-Eddington accretion episode is violent. Shockwaves propagate through the interstellar medium at thousands of kilometers per second. They sweep up gas, compress it, heat it to millions of degrees. The expanding bubble of shocked gas is visible in X-rays as a hot cavity in the surrounding cooler material. And it is visible in radio as synchrotron emission from cosmic rays accelerated at the shock front. The radio bubbles are the remnants of such an outburst. They mark the extent of the blast, the volume cleared out by the black hole's wind. Inside the bubbles, the gas is hot and tenuous, heated by the passage of the shockwave. Outside, the gas is cooler and denser, the ambient interstellar medium that has not yet been affected. The bubble walls themselves are shell-like structures where the expanding outflow is compressing the surrounding gas, creating the bright radio emission observed by Meerkat. But the bubbles are not smooth, they are threaded with structure. Filamentary emission pervades the interior. Some of these interior filaments are undoubtedly part of the vertical filament population, structures that existed before the outburst, illuminated by the cosmic rays injected during the event. Others might be instabilities in the bubble walls. Rayleigh-Taylor fingers, created as the hot interior gas tries to buoyantly rise through the cooler exterior. The connection between the radio bubbles and the filaments is not just spatial, it is temporal. The age estimates for both structures overlap: 6 million years. This cannot be coincidence. The same event that inflated the bubbles must have created or illuminated the filaments. The outburst from Sagittarius A star was not just a single pulse of energy. It was a sustained wind that lasted for perhaps millions of years. During this time, the black hole continuously injected cosmic rays into the galactic center environment. These particles flowed along magnetic field lines, filling flux tubes, creating the glowing threads we observe as radiofilaments. The vertical orientation of most filaments makes sense in this context. The outflow from Sagittarius A star was primarily directed perpendicular to the accretion disk, along the rotation axis. The magnetic field in this outflow would have been organized by the rotation of the accretion disk and by the geometry of the wind. Field lines would have been stretched vertically, pulled away from the galactic plane by the expanding bubble. Cosmic rays accelerated at the base of the outflow would stream along these vertical field lines, illuminating them, creating vertical filaments that tower above and below the disk. The horizontal filaments discovered in 2023 fit into this picture as well. They are concentrated on one side of Sagittarius A star, pointing radially toward the black hole. This asymmetry suggests that the outflow had a component along the galactic plane, not just vertically. Perhaps the accretion disk was tilted slightly. Or perhaps the vertical outflow collided with the dense molecular material in the disk, creating a secondary flow that spread laterally. Along the plane, this horizontal outflow would have swept past molecular clouds and H2 regions, compressing them, stretching them, creating the radial pattern of filaments pointing back toward their source. The different populations of filaments might therefore represent different phases or different components of the same outburst event. The vertical filaments trace the primary bipolar wind. The horizontal filaments mark the secondary lateral flow created when the wind interacted with the disk. Both populations are approximately the same age. Both contain cosmic rays accelerated during the outburst, but they probe different aspects of the three-dimensional flow structure. This interpretation makes Sagittarius A star the central actor in the galactic center drama. Not a passive gravitational anchor, but an active source of energy that periodically reshapes its surroundings. The black hole has been quiet for the few centuries humans have been observing it with telescopes. But on timescales of millions of years, it alternates between quiescence and violence. Most of the time, it accretes slowly, barely glowing. Then, every few million years, something triggers a major outburst. The accretion rate spikes. The black hole becomes an engine of destruction. driving winds that clear out vast regions of space, accelerating particles to relativistic energies, inflating bubbles that dwarf the entire stellar disk of our galaxy. And then it goes quiet again. The fuel supply dwindles, the wind shuts off, the bubbles expand and fade. The filaments gradually lose their cosmic ray population as particles radiate away their energy. The system relaxes, waits, accumulates new material. Until the next perturbation triggers the next outburst, the cycle repeats, has repeated many times over the history of our galaxy. Each outburst leaves behind signatures, bubbles, filaments, shells of swept-up gas, layered atop the remnants of previous events, creating the complex, multiply-shocked structure we observe in the galactic center today. The 6 million year age estimate means the last major outburst occurred when Earth was very different. The Miocene epoch. Our hominin ancestors had not yet split from the great apes. The Mediterranean Sea did not exist. It was a dry basin. Africa and Europe were connected by land. South America and Antarctica had recently separated, opening the Drake Passage and establishing the Antarctic Circumpolar Current. This current isolated Antarctica thermally, leading to the formation of the ice sheets that cover the continent today. While these geological changes reshaped Earth's surface, something equally dramatic was occurring at the center of our galaxy. 26,000 light-years away, invisible to any organism on Earth's surface. Sagittarius A star erupted. For hundreds of thousands of years, it blazed with a luminosity millions of times its current value. The outburst pumped 10 to the 56 ergs into the surrounding space, enough energy to unbind the entire central molecular zone, to blow away all the gas within hundreds of parsecs of the black hole. But the gas did not escape. It was swept outward, shocked, heated. But held by the deep gravitational potential well of the galactic center, it accumulated in shells, compressed, cooled, formed new molecular clouds, which, in turn, formed new stars. The outburst did not sterilize the galactic center. It transformed it, reset it, cleared out old structures, and created conditions for new ones to form. This cycle of destruction and creation is not unique to the Milky Way. All galaxies with supermassive black holes undergo similar episodes. Active galactic nuclei represent the extreme examples. Black holes accreting at near Eddington rates continuously, driving powerful jets that extend for millions of light-years into intergalactic space. These jets contain more energy than entire galaxy clusters. They reshape the intergalactic medium, suppress galaxy formation across volumes larger than our local group. But even quiescent galaxies like the Milky Way show evidence of past activity. Most supermassive black holes spend most of their time dormant, accreting slowly. But periodically they activate. The duty cycle is uncertain. Perhaps 10% of the time, perhaps 1%, but over billions of years, every supermassive black hole goes through multiple active phases. Each phase leaves behind traces. Bubbles, filaments, shocked gas. These traces fade over tens of millions of years. But if you observe at the right time, within a few million years of an outburst, you can see them. Fresh. Still glowing. We are observing the Milky Way at exactly the right time. The outburst occurred recently enough that the signatures remain visible. The radio bubbles have not yet dissolved into the surrounding medium. The filaments still shine with synchrotron emission from cosmic rays that have not yet radiated away their energy. In another 10 million years, these structures will be gone. The bubbles dispersed, the filaments faded to invisibility. Future astronomers studying the galactic center 10 million years from now will find no evidence of the outburst we are witnessing the aftermath of today, unless they look very carefully at faint shells and diffuse emission that might be the heavily degraded remnants. By 100 million years from now, even those traces will have vanished. The galactic center will appear quiescent. Until the next outburst resets the clock, the filaments are therefore not permanent features of the galactic center, they are transient. Temporary structures that appear after outbursts and fade over millions of years. The fact that we see so many filaments suggests either that we are observing shortly after an unusually energetic outburst that created an exceptional number of structures, or that multiple outbursts have occurred over the past 10 million years, each contributing filaments at different stages of evolution. The age estimates based on synchrotron losses give a characteristic age of 6 million years. But this is the age of the cosmic ray electrons, not necessarily the age of the magnetic structures themselves. The flux tubes might be older, relics of even earlier outbursts, only recently re-illuminated by fresh cosmic rays from the most recent event. Sagittarius A star is not just the gravitational center of our galaxy. It is the energy center, the engine that periodically injects enormous quantities of energy into its surroundings, reshaping the galactic center environment, regulating star formation, enriching the halo with metals from stars that formed in previous cycles. The black hole is not a dead endpoint. It is an active participant in galactic evolution, and the filaments are its signature, the visible evidence of its power. The scars it leaves on the magnetic structure of space itself. For 40 years, scientists have proposed theories to explain the galactic center filaments. Every theory explains something. None explains everything. The theories rise, gain support, then collapse under the weight of observations they cannot accommodate. The wreckage of failed hypotheses litters the scientific literature, each one a testament to how profoundly these structures violate our understanding of astrophysical processes. The first theory proposed in the 1980s was the simplest. The filaments trace the Milky Way's global magnetic field. Galaxies have magnetic fields. This is well established. The fields are generated by dynamo processes in the rotating disk. Differential rotation winds up field lines. Supernova-driven turbulence amplifies them through small-scale dynamo action. The result is a large-scale organized field with strength around a few microgauss, pervading the entire galactic disk. In the disk, the field runs parallel to the plane, following the spiral arms. But above and below the disk, in the halo, the field can adopt different orientations. Models predicted that vertical field components should exist near the galactic center, rising buoyantly from the disk. The vertical orientation of the original filaments fit this picture perfectly. They could be magnetic flux tubes anchored in the disk and extending into the halo, made visible by cosmic rays illuminating the field lines. This theory had appeal. It connected the filaments to a known component of galactic structure. It explained their vertical orientation. It accounted for their persistence. Global magnetic fields do not change rapidly. They evolve over hundreds of millions of years, long enough for the filaments to remain stable. But the theory died when Meerkat discovered the faint filaments. Many of these structures are not vertical. They orient randomly, some at 45 degrees to the plane, others nearly horizontal. If the filaments trace the global field, they should all share similar orientations. The random orientations of the faint filaments proved the global field hypothesis was wrong. The filaments are local structures, not tracers of galaxy-scale fields. The second theory was more exotic. The filaments are cosmic strings, topological defects in space-time left over from the Big Bang. In the first fractions of a second after creation, the universe underwent phase transitions. As it cooled, symmetries broke. Some theories predicted that these symmetry-breaking events would create defects. One-dimensional defects called cosmic strings. Two-dimensional defects called domain walls. Point-like defects called monopoles. Cosmic strings would be incredibly thin, smaller than an atomic nucleus, but incredibly massive. Linear mass densities around 10 to the 21 kilograms per meter. A cosmic string 1 meter long would weigh more than Mount Everest. If cosmic strings exist, they would be essentially indestructible. They cannot break or merge easily. They oscillate at relativistic speeds, vibrating like plucked guitar strings across cosmic distances. The cosmic string hypothesis explained the filaments' thinness, why they appeared one-dimensional even when observed with the highest resolution telescopes. It explained their persistence. Cosmic strings do not decay. They exist indefinitely. And it explained the extreme magnetic field strengths. A cosmic string passing through the galaxy would attract and accumulate magnetic flux, creating the intense fields observed in the filaments. Farhad Yousafzadeh seriously considered this possibility in the late 1980s. The properties seemed to match. But problems emerged. Cosmic strings should oscillate, move. The galactic center filaments show no motion. Observations separated by decades show them in identical positions. Cosmic strings should be straight on small scales. The filaments curve, branch, show complex morphology inconsistent with fundamental topological defects. The final blow came when high-resolution observations revealed that some filaments split. A single thread dividing into two. Cosmic strings cannot split. They are topologically protected. They can intersect and exchange partners. But a single string cannot break into fragments. The observation of splitting filaments ruled out cosmic strings conclusively. By the mid-1990s, the theory was abandoned. The third theory invoked magnetic reconnection. When oppositely directed magnetic field lines encounter each other in a plasma, they can reconnect. The field lines snap together, rearrange into lower energy configurations. The magnetic energy released during reconnection converts into kinetic energy, heating the plasma, accelerating particles, creating explosive releases of energy. Magnetic reconnection is well observed in solar flares. On the Sun, field lines in the corona reconnect, releasing energy equivalent to billions of nuclear weapons in seconds. The energy heats plasma to tens of millions of degrees, accelerates particles to near relativistic speeds, and creates bright flashes of X-rays and radio waves. If similar processes occur in the galactic center, they might create filamentary structures, elongated current sheets where reconnection is actively occurring. The theory explained several features. The synchrotron emission. Reconnection accelerates electrons to the energies needed to produce the observed radio emission. The magnetic field orientation. Reconnection current sheets naturally have fields aligned along their length, and the presence of multiple filaments. If the galactic center magnetic field is tangled, many reconnection sites could exist simultaneously. But reconnection creates sheet-like structures, not threads. Current sheets are two-dimensional. They have length and width but negligible thickness. The galactic center filaments are one-dimensional. They have length but appear equally thin in both transverse directions. Additionally, reconnection is transient. Individual reconnection events last minutes to hours. Even if multiple events occur in sequence, the timescales are far too short to explain structures that persist for millions of years. Magnetic reconnection might contribute to the physics of the filaments, but it cannot be the primary formation mechanism. The fourth theory involves supernova-driven winds and instabilities. The galactic center contains massive stars. These stars explode as supernovae. The explosions create expanding shells of shocked gas and amplified magnetic field. Multiple supernovae occurring in the same region could create a superbubble, a cavity blown in the interstellar medium by the cumulative energy of many explosions. The galactic center's star formation rate is high enough that superbubbles should exist. When a superbubble expands, it compresses the surrounding magnetic field. The compressed field can reach strengths 10 to 100 times higher than the ambient field. If cosmic rays accumulate in the compressed regions, they illuminate the field, creating bright filaments along the compressed flux tubes. The bubble walls become visible as filamentary structures. This theory explained the association between filaments and star-forming regions. Many filaments appear near massive star clusters. It explained the typical field strengths. Compression by factors of 10 matches observations. And it explained the synchrotron emission. Supernova remnants are known cosmic ray accelerators. But supernovae create spherical or mildly elliptical structures, not long linear filaments. The aspect ratios are wrong. Supernova remnants are perhaps twice as long as they are wide. The galactic center filaments have aspect ratios exceeding 100 to 1. They are far too elongated to be supernova-driven structures. Some filaments might be associated with supernova remnants, but the majority require a different explanation. The fifth theory is currently the leading candidate: cosmic ray-driven instabilities, specifically the streaming instability. This mechanism operates whenever cosmic rays flow faster than the alpha wave speed, the speed at which magnetic disturbances propagate through magnetized plasma. When streaming occurs, the cosmic rays excite waves in the plasma. These waves scatter the cosmic rays, slowing them down, but the wave energy comes from the cosmic ray kinetic energy. The magnetic field grows. The process is self-regulating. The amplified magnetic field increases the Alfvén speed. Eventually, the cosmic ray streaming velocity and the Alfvén speed become equal. At this point, the instability saturates. The field stops growing. The system reaches a quasi-equilibrium state where cosmic rays stream along field lines at exactly the local Alfvén speed, continuously generating waves that scatter them and maintain the magnetic field at elevated strength. This mechanism naturally creates filamentary structures. Cosmic rays flow preferentially along magnetic field lines. The streaming instability amplifies the field along these preferred paths, creating enhanced field flux tubes embedded in a weaker ambient field. The filaments are not separate structures. They are regions where the field has been amplified by cosmic ray streaming. Theoretical calculations show that streaming instability can amplify magnetic fields by factors of 10 to 100. Matching observations. It operates over timescales of millions of years, matching the inferred ages of the filaments. And it requires no special initial conditions. Any cosmic ray population flowing through a magnetized plasma will drive the instability if the streaming velocity exceeds the Alfvén speed. Numerical simulations of cosmic ray transport in the galactic center environment produce filamentary structures when streaming instability is included. The simulations cannot reproduce all observed properties. The precise spacing between filaments, the extreme lengths of the longest structures, but they demonstrate that the basic mechanism is viable. Cosmic rays and magnetic fields interacting through streaming instability can create visible filamentary patterns. But even the streaming instability theory struggles with certain observations. The regularity of filament spacing in groups, the harp-like arrangements with equally spaced parallel threads. Streaming instability does not predict such precise geometric organization. It creates filaments wherever cosmic rays are streaming. The resulting structures should be more randomly distributed, not organized into groups with characteristic separations. Some researchers have proposed that the spacing might result from the characteristic wavelength of the fastest-growing instability mode. But this wavelength depends on the plasma properties, density, temperature, magnetic field strength. These vary throughout the galactic center. The instability wavelength should vary correspondingly. Yet the observed filament spacing is remarkably constant within each group. This suggests an additional organizing principle beyond streaming instability alone. Another puzzle is the extreme thinness of the filaments. Streaming instability amplifies fields along preferred directions, but it does not inherently create one-dimensional structures. The amplified regions should have some transverse extent, determined by diffusion and turbulent mixing. Yet the observed filaments appear truly one-dimensional, thinner than any process involving plasma physics should naturally produce. This suggests that additional physics may be operating, something that confines the structures to widths far smaller than diffusion would allow. The comparison with filaments in other galaxies provides additional constraints. Meerkat and other radio telescopes have discovered similar filamentary structures in several nearby galaxies. Notably, in the Circinus galaxy, NGC 253 and M82. These are starburst galaxies, regions undergoing intense star formation driving powerful galactic winds. The filaments in these galaxies share properties with Milky Way filaments. Similar lengths, similar radiospectral indices, similar orientations relative to the galactic disk. This suggests that galactic center filaments are not unique to the Milky Way. They are a generic feature of galactic nuclei with active star formation or active black holes. The mechanism creating them operates universally. This universality argues against explanations that rely on special circumstances unique to our galaxy. The correct theory must explain why filaments appear generically whenever the right conditions exist. High cosmic ray fluxes, strong magnetic fields, turbulent environments, active energy injection. But the existence of filaments in other galaxies also reveals differences. The filaments in M82 appear more chaotic than those in the Milky Way, less organized. No harp-like structures. The filaments in NGC 253 are shorter on average. The differences might reflect environmental variations. different magnetic field geometries, different cosmic ray sources. Or they might indicate that multiple formation mechanisms operate, creating superficially similar structures through distinct physical processes. Every theory captures part of the truth. The global magnetic field shapes the large-scale environment. Cosmic strings are irrelevant, but magnetic flux tubes are real. Magnetic reconnection contributes energy. Supernova compression creates local amplifications. Streaming instability organizes cosmic rays and fields. The filaments likely result from the complex interplay of all these processes, operating simultaneously in the chaotic galactic center environment. But this complexity frustrates understanding. If multiple mechanisms contribute, how do you separate their effects? How do you determine which process dominates? The observations show the final result, the product of millions of years of evolution involving dozens of physical processes. Untangling the contributions of each process from a single snapshot requires assumptions, models, simulations, each with their own uncertainties. The filaments remain fundamentally mysterious despite 4 decades of intensive study. We know what they are made of: magnetic fields and cosmic rays. We know approximately how old they are, a few million years. We know where they are, in and around the central molecular zone. But we do not know exactly how they form, why they adopt their particular geometries, or what determines which regions of the galactic center develop filaments while others remain dark. The answer likely involves initial conditions we cannot observe. The magnetic field geometry before the last outburst from Sagittarius A star, the distribution of molecular clouds at that time, the locations of supernova explosions over the past 10 million years. All of these factors shape the environment in which filaments form. All are lost to history. We see only the present state, the current configuration of structures that survived the turbulent evolution of the galactic center, the fossils rather than the living processes that created them. This is the essential frustration of observational astrophysics. We cannot rewind time. We cannot watch the filaments form. We see a single moment in a process that unfolds over millions of years. From this frozen instant, we must reconstruct the entire history, infer the dynamics from the static structure, imagine motion from stillness. It is like trying to understand an entire war from a single photograph of a battlefield. You can see the positions of the forces, the damage inflicted, but the tactics that led to this configuration, the decisions made by the commanders, the sequence of events, all remain invisible, locked in the past, accessible only through theory and imagination. Every second, cosmic rays rain down on Earth. Millions of them. Protons traveling at 99.99% the speed of light. Helium nuclei. Heavy ions. They slam into the upper atmosphere, collide with nitrogen and oxygen molecules, shatter into cascades of secondary particles, muons, pions, electrons. These secondary particles reach the surface, pass through your body. Right now, as you sit there, approximately 1 cosmic ray-induced muon penetrates your body every second. You do not feel it. It leaves no trace. But it happens, has happened since you were born, will continue until you die. Most cosmic rays originate from supernova explosions in our galaxy. When a massive star dies, it does not go quietly. The core collapses, rebounds, drives a shock wave through the stellar envelope. The shock wave accelerates particles, protons, electrons, heavy nuclei, launching them into interstellar space at relativistic velocities. These particles wander through the galaxy for millions of years, bouncing off magnetic irregularities, diffusing slowly outward, eventually reaching Earth. The cosmic ray energy spectrum follows a power law. At low energies, around 1 billion electron volts, there are many cosmic rays. At higher energies, the flux decreases. By 100 billion electron volts, there are 1,000 times fewer particles. By 1 trillion electron volts, 1,000,000 times fewer. The spectrum drops steeply, but it never reaches zero, even at energies exceeding 10 to the 20 electron volts. 100 million trillion electron volts. Cosmic rays exist. Impossibly energetic particles. Single protons carrying more kinetic energy than a professionally thrown baseball. Where do the highest energy cosmic rays come from? Not supernovae. Supernova remnants can accelerate particles to perhaps 10 to the 15 electron volts. Maybe 10 to the 16 if conditions are optimal. Beyond that, the particles escape. The magnetic fields in supernova remnants cannot confine them. They leak out before reaching higher energies. The ultra-high energy cosmic rays must come from more exotic sources. Active galactic nuclei. Gamma-ray bursts. Possibly supermassive black holes like Sagittarius A star during outbursts. The galactic center filaments contain cosmic rays in a specific energy range, between 1 billion and 100 trillion electron volts. This is the sweet spot for producing radiosynchrotron emission in 100 microgauss magnetic fields. Lower energy particles emit at frequencies below what radio telescopes detect. Higher energy particles emit at X-ray and gamma-ray frequencies. The radio emission traces particles in this intermediate range, energetic enough to produce copious radiation, but not so energetic that they escape confinement. The total number of cosmic ray electrons in a filament can be estimated from the observed synchrotron luminosity. For a typical filament emitting radio power around 10 to the 34 ergs per second, the calculation gives approximately 10 to the 48 electrons above 1 billion electron volts. That is 10 trillion electrons. Each one spiraling through the magnetic field, each one radiating. Together, they make the invisible visible. The magnetic field glows. But electrons lose energy rapidly through synchrotron radiation. An electron at 10 billion electron volts in a 100 microgauss field radiates away half its energy in 100,000 years. The lifetime is energy dependent. Higher energy electrons lose energy faster. They radiate more intensely, burn out more quickly. The electron population in a filament is therefore constantly evolving. The highest energy electrons disappear first, then progressively lower energy electrons fade. The spectrum steepens. The emission dims. This synchrotron aging process limits the visibility time of filaments. Without continuous injection of fresh electrons, a filament would fade from view within a few million years. The fact that we observe filaments implies active injection. Something is continuously replenishing the electron population, preventing the structures from fading into darkness. This something must operate over millions of years, longer than individual supernova remnants shine, longer than stellar winds from single massive stars blow. Only sources with long duty cycles can maintain the electron populations. Sagittarius A star during an extended outburst provides such a source. For hundreds of thousands or millions of years, the black hole drives a wind. The wind contains turbulence, shocks, magnetic reconnection sites. All of these features can accelerate particles, not to the ultra-high energies, but to the intermediate energies needed to produce radio emission. The accelerated electrons flow along magnetic field lines, filling flux tubes throughout the galactic center, creating the population of filaments we observe. But electron acceleration is only part of the story. The cosmic rays also include protons. In fact, protons dominate. For every cosmic ray electron, there are approximately 100 cosmic ray protons at similar energies. Protons do not produce synchrotron emission efficiently at radio frequencies. Their mass is nearly 2,000 times greater than electrons. For a given energy, they spiral much more slowly through magnetic fields. The radiation frequency scales inversely with particle mass squared. Protons emit at frequencies 4 million times lower than electrons of the same energy. Their synchrotron radiation lies in the extremely low frequency radio band, below what any telescope can observe. The cosmic ray protons are therefore invisible. But they exist. They must exist. The same acceleration processes that create relativistic electrons necessarily create relativistic protons. With higher efficiency, protons are more massive. They carry more momentum. They couple more strongly to collective plasma processes. In supernova remnant shocks, approximately 99% of the accelerated energy goes into protons, only 1% into electrons. If this ratio holds in the galactic center, then for every electron we observe emitting synchrotron radiation, there are 100 protons at similar energies. Invisible, undetected, but present. The total energy in cosmic ray protons throughout the galactic center must therefore exceed the electron energy by factors of hundreds or thousands. The electrons contain approximately 10 to the 50 ergs. The protons must contain 10 to the 52 or 10 to the 53 ergs. This is more energy than is contained in the thermal motions of all the gas in the central molecular zone. More than the gravitational binding energy of molecular clouds, cosmic rays are not a minor component of the galactic center energy budget. They are a dominant component, possibly the dominant component, shaping the dynamics, regulating star formation, driving outflows. Cosmic ray protons interact with the interstellar medium differently than electrons. Protons do not lose energy through synchrotron radiation in the weak interstellar magnetic fields. Their lifetimes are limited not by radiation losses but by collisions with gas. When a cosmic ray proton strikes a gas nucleus, it can create pions, short-lived particles that decay into gamma rays. These gamma rays are detectable. The Fermi Gamma Ray Space Telescope has mapped the galactic center at gamma ray energies. It detects extended emission, not from a point source, but from a diffuse glow pervading the central molecular zone. This gamma ray emission traces cosmic ray protons colliding with molecular gas, producing the high-energy photons through pion decay. The intensity of the gamma ray emission depends on both the cosmic ray density and the gas density. Regions with high gas densities and high cosmic ray densities produce bright gamma ray emission. Regions with low densities produce faint emission. By mapping the gamma ray intensity and comparing it with gas density measurements from molecular line observations, astronomers can infer the cosmic ray density distribution. The results show that cosmic rays are not uniformly distributed. They concentrate in certain regions, notably near Sagittarius A star, and along the trajectories of the radiofilaments. This correlation between gamma ray emission and radiofilaments provides independent evidence that the filaments contain enhanced cosmic ray densities. The radio emission traces electrons. The gamma ray emission traces protons. Both show enhancements in the same locations. This confirms that the filaments are not just magnetic structures made visible by a chance population of electrons. They are genuine cosmic ray transport channels, pathways along which both protons and electrons flow. The cosmic ray protons have longer lifetimes than electrons. They do not radiate away their energy. They can persist for tens of millions of years, slowly diffusing through the interstellar medium, colliding occasionally with gas nuclei, producing gamma rays, gradually losing energy through these collisions, eventually thermalized. Their kinetic energy converted into heat, but the process is slow. Cosmic ray protons are long-lived tracers of past acceleration events. They carry information about conditions in the galactic center over much longer timescales than the electrons. The cosmic ray electrons visible in the filaments today were accelerated relatively recently, within the past few million years. Otherwise, they would have radiated away their energy. But the cosmic ray protons could have been accelerated tens of millions of years ago. They persist, wander, fill larger volumes. The proton population we observe today might include contributions from multiple generations of acceleration events, multiple outbursts from Sagittarius A star, multiple supernovae, all mixed together into a single cosmic ray sea filling the entire galactic center. Disentangling these contributions is nearly impossible. Cosmic ray protons do not carry information about where or when they were accelerated. They diffuse, lose their directional information, mix thoroughly with cosmic rays from other sources. Only their energy spectrum retains clues. The shape of the spectrum depends on the acceleration mechanism and the time since acceleration. But multiple sources with different acceleration efficiencies in different ages can produce similar spectral shapes. The degeneracy is severe. The cosmic rays in the filaments are therefore messengers, but their message is partially obscured. encrypted by millions of years of propagation through turbulent magnetic fields. We can read some of the text. The particles were accelerated to high energies. They flowed along magnetic field lines. They illuminated flux tubes that we now observe as radiofilaments. But the details remain fuzzy. Which specific acceleration events contributed which particles? How did the particles propagate from their sources to the filaments? How long ago did acceleration occur? These questions have no definitive answers. Only models, simulations, educated guesses. The cosmic ray spectrum observed from Earth provides some constraints. The spectrum measured by ground-based detectors and balloon-borne instruments shows a Ni around 10 to the 15 electron volts. Below the Ni, the spectrum follows a single power law. Above the Ni, it steepens, breaks to a different power law. This Ni is believed to mark the transition between galactic cosmic rays accelerated by supernova remnants and extragalactic cosmic rays from more distant sources. The galactic accelerators cannot boost particles beyond the Ni. They escape, leave the galaxy, never return. But the galactic center environment is more extreme than the general galactic disk. Magnetic fields are stronger, gas densities higher, energy injection more intense. Perhaps galactic center sources can accelerate particles beyond the Ni to 10 to the 16 electron volts, 10 to the 17. The magnetic field strengths in the filaments are certainly sufficient to confine particles at these energies. Fields of 100 microgauss can confine protons up to 10 to the 17 electron volts in structures tens of parsecs across. The geometry allows it. The question is whether acceleration mechanisms exist that can actually boost particles to these energies. Sagittarius A* during a super Eddington outburst is a plausible candidate. When a supermassive black hole accretes at near maximum rates, the environment becomes extraordinarily violent. Magnetic fields amplify through dynamo action to strengths exceeding 1,000 Gauss near the event horizon. Turbulence accelerates particles through second-order Fermi acceleration. Magnetic reconnection produces particle acceleration in current sheets. Shocks in the outflow boost particle energies through first-order Fermi processes. All of these mechanisms operating simultaneously in an extreme environment might produce ultra-high energy cosmic rays, particles at or beyond the Ni, detectable only in the most sensitive cosmic ray experiments. Some researchers have speculated that the galactic center is the dominant source of cosmic rays at Earth, not supernovae scattered throughout the disk, but Sagittarius A* during periodic outbursts, injecting enormous quantities of high-energy particles into the galaxy. These particles diffuse outward, fill the galactic halo. Some eventually reach the solar system. The cosmic rays striking Earth would therefore be messages from the galactic center. Photons from past outbursts, frozen in energy, carrying information about conditions at the galaxy's heart millions of years ago. This hypothesis is controversial. Most cosmic ray physicists believe supernovae are sufficient to explain the observed cosmic ray population. No need to invoke exotic sources at the galactic center. But the hypothesis is not easily ruled out. If Sagittarius A* contributes even 10% of the galactic cosmic ray population, its influence is significant. And during outbursts, its contribution might spike to 50% or more, briefly dominating the cosmic ray flux, before fading as the outburst ends and the injected particles diffuse through the galaxy. The filaments provide direct evidence that the galactic center accelerates cosmic rays efficiently. The synchrotron emission is unambiguous. Relativistic electrons exist in large numbers, with energies reaching trillions of electron volts. If electrons are accelerated to these energies, protons must be accelerated to similar or higher energies. The acceleration mechanisms do not discriminate. They operate on all charged particles, with efficiencies that favor protons over electrons. The galactic center is not just a source of radio-emitting filaments. It is a cosmic ray factory, perhaps the most powerful in the galaxy. Every cosmic ray electron in the filaments is screaming, radiating, losing energy, dying slowly, its lifetime measured in thousands or millions of years. But during that lifetime, it serves as a tracer, marking the location of magnetic field lines, revealing structure otherwise invisible. When the electron finally radiates away all its energy, it joins the thermal population, just another electron in the plasma, indistinguishable from those created in stellar atmospheres or ionized by ultraviolet radiation. Its history erased, but for a brief moment, cosmologically speaking, it glows. And in that glow, we see the skeleton of the galactic center, the magnetic architecture, the invisible made visible through the sacrifice of particles that refuse to die quietly. We have studied the filaments for 40 years, built better telescopes, developed sophisticated theories, accumulated terabytes of data, and we still do not understand them. Not fundamentally, not completely. Every answer generates 3 new questions. Every observation reveals more complexity. The mystery deepens rather than resolves. The most basic question remains unanswered. How do you create a structure 150 light-years long and less than 1 light-year wide that persists for millions of years in a turbulent environment? Nothing in our experience prepares us for such geometry. On Earth, long, thin structures require rigid materials, steel beams, carbon fiber, materials that resist bending and breaking. But the filaments are not made of matter. They are magnetic fields and cosmic rays, configurations of invisible forces that somehow maintain coherence across distances that light takes 150 years to traverse. The streaming instability theory provides a mechanism for amplifying magnetic fields along preferred directions. But it does not explain why the amplified regions remain so extraordinarily narrow. Diffusion should broaden them. Turbulence should tangle them. Instability should disrupt them. Yet the filaments remain threads. One-dimensional structures in three-dimensional space. The confinement mechanism remains unknown. The regular spacing between filaments and groups poses another fundamental puzzle. Why 16 arcseconds between threads in one group? Why 12 arcseconds in another? These spacings are not random. Within each group, the separation is remarkably constant. This implies a characteristic scale, some physical process that naturally produces structures separated by specific distances. But what process operates on scales of tenths of a parsec in the galactic center environment? One possibility is that the spacing reflects the wavelength of magnetic oscillations. Alpha waves propagating through magnetized plasma have characteristic wavelengths determined by the field strength and plasma density. If multiple filaments formed simultaneously from the same oscillating magnetic structure, they might naturally adopt spacings equal to the wavelength. But this explanation requires fine-tuning. The plasma properties must be precisely uniform across tens of parsecs to produce constant spacing. The galactic center is not uniform, it is chaotic, variable, inhomogeneous. The extreme lengths of the filaments create timing problems. If the vertical filaments formed during the outburst from Sagittarius A star 6 million years ago, how did they grow so long? The outflow velocity from the black hole was perhaps a few thousand kilometers per second. At that speed, material travels 1 parsec in roughly 300 years. To create a 100 parsec filament requires 30,000 years of continuous outflow. This is plausible, but it assumes the outflow maintained a constant direction. Any variation in direction would create curved structures. The straightness of many filaments suggests the outflow was remarkably collimated, maintaining a fixed direction for tens of thousands of years. This level of stability is unexpected for an accreting black hole with a turbulent disk. The connection between vertical and horizontal filaments remains unclear. Are they distinct populations formed by separate processes, or do they represent different evolutionary stages of the same structures? The horizontal filaments might be fragments of vertical filaments broken and reoriented by lateral flows. But the details are murky. How does a magnetic flux tube break? What happens to the cosmic rays when the field topology changes? Do they escape, or do they remain confined, marking the new orientation of the fragmented structure? The asymmetry of the horizontal filaments is unexplained. Why do they concentrate on one side of Sagittarius A star? The lateral outflow model suggests an asymmetric interaction between the vertical outflow and the disk. But why asymmetric? Was the disk denser on one side? Was the outflow stronger in one direction, or is the asymmetry just an accident of our viewing angle? Perhaps the horizontal filaments exist on both sides, but we can only see one population clearly due to foreground absorption or geometric projection effects. The age estimates for the filaments carry large uncertainties. The 6 million year number comes from synchrotron aging calculations, but these calculations assume the electron energy distribution has not changed since injection. They assume no reacceleration, no fresh particle injection. If cosmic rays are continuously accelerated or re-energized within the filaments, the age estimates are wrong. The structures could be much older or much younger. The electrons we observe might not trace the initial formation epoch. They might represent recent activity superimposed on much older magnetic structures. The relationship between the filaments and star formation is ambiguous. Some filaments clearly associate with young massive star clusters. Others appear isolated from any identifiable stellar populations. Does star formation trigger filament formation? Or do filaments channel gas flows that enhance star formation? Causality is difficult to establish from a single snapshot in time. Both processes might occur, creating a feedback loop where filaments influence star formation and star formation modifies filaments. Disentangling cause and effect requires time domain observations. Watching the structures evolve, seeing how they respond to changes in their environment. The total mass of material in the filaments is negligible. The magnetic energy and cosmic ray energy are enormous, but the actual matter, the electrons and protons and any associated gas, amount to perhaps a few thousand solar masses spread across hundreds of structures. This is less than 1% of the gas mass in the central molecular zone. The filaments are not gravitationally significant. They do not bind gas. They do not affect stellar orbits. They are energetically important but dynamically minor. Ghosts in the machine, visible but insubstantial. The gamma-ray emission from the galactic center constrains the cosmic ray population but does not uniquely determine it. The observed gamma-ray intensity is consistent with a wide range of cosmic ray densities and spectra. The degeneracy between source luminosity and distance creates additional ambiguity. Are there a few bright cosmic ray sources, or many faint ones? The gamma rays alone cannot distinguish these scenarios. Combined with the radio observations, constraints tighten, but large uncertainties remain. The magnetic field geometry on large scales remains poorly mapped. We see the filaments, the brightest field lines. But what about the weaker fields between filaments? How does the large-scale field connect to the small-scale flux tubes? Is the field topology simple, a smooth global structure with localized enhancements, or complex? A tangled web where every scale couples to every other scale? Current observations cannot resolve this. We lack the sensitivity to map faint diffuse emission. We see peaks, not valleys, highlights, not shadows. Future observations will help. The square-kilometer array is under construction in Australia and South Africa. When completed, it will be 50 times more sensitive than MeerKAT. It will detect filaments too faint for current telescopes. Map diffuse emission between the bright structures. Measure polarization with unprecedented precision. The next generation Very Large Array is planned for the Western United States, another factor of 10 improvement in sensitivity and resolution. These instruments will transform our view of the galactic center. Reveal structure we cannot currently imagine. But instruments alone do not guarantee understanding. Better data creates better constraints. Tighter error bars. More secure detections. But physical insight requires theory, models, simulations that connect observations to underlying processes. And theory is hard. The equations governing magnetized plasma are nonlinear, coupled, intractable except in special cases or through numerical approximation. Simulations can explore parameter space, test hypotheses, but they are limited by computational resources and by our understanding of which physics to include. The galactic center is a laboratory for extreme astrophysics. Nowhere else in the nearby universe can we study supermassive black hole outflows at such high resolution, observe magnetic structures in such detail, probe cosmic ray acceleration in such an energetic environment. The filaments are unique in our observational reach. Other galaxies harbor similar structures, but they are far away, blurred by distance, unresolved. Only in the Milky Way can we see individual filaments, measure their properties, study their evolution. But we are also limited by perspective. We see the galactic center from one location, one angle. The three-dimensional structure projects onto two dimensions. Distances along the line of sight are ambiguous. Is a filament 10 parsecs long seen end-on? Or 100 parsecs long seen at a shallow angle? Radial velocity measurements help, but they provide only one component of the three-dimensional velocity field. The full picture remains hidden, obscured by geometry. The intellectual humility required to study the filaments is profound. We must acknowledge how little we know. How much remains mysterious. 40 years of research has revealed complexity, not simplicity. The filaments do not fit into neat theoretical boxes. They are messy, multifaceted. Products of processes we glimpse only partially. Every paper published adds to our knowledge, but also to our list of unsolved problems. Progress is real, but slow, incremental. Each generation of astronomers pushes understanding forward by small steps, not giant leaps. The filaments force us to confront the limitations of human intuition. Our brains evolved to navigate a world of solid objects at human scales. We understand ropes and wires and cables, things we can touch. The filaments are none of these. They are invisible structures at scales billions of times larger than anything in human experience. Persisting for time spans millions of times longer than human history, operating through processes we have never directly observed. Our intuition fails. We must rely on mathematics, on abstract reasoning, on analogies to laboratory plasmas that capture some features but miss others. This is the essential challenge of astrophysics. We cannot perform experiments, cannot change parameters, cannot rerun events to see what happens differently. We observe, we measure, we infer. The universe provides one realization of a vast possibility space. From this single example, we try to extract general principles, laws of nature that apply everywhere. But how do we know our galaxy is typical? How do we know the filaments we observe represent the norm rather than an exception? Statistical arguments help. If filaments appear in multiple galaxies, they are probably generic. But the sample is small, perhaps dozens of galaxies, out of hundreds of billions. The concern always lurks. Are we generalizing from a special case? The filaments teach us about magnetic fields and cosmic rays and plasma physics. But they also teach us about the nature of scientific knowledge itself, how we build models from incomplete data, how we test theories when experiments are impossible, how we navigate uncertainty while still making progress. The filaments are a case study in the epistemology of observational science. The methods we develop to understand them apply broadly to other astrophysical problems, to other domains where direct manipulation is impossible and inference is everything. They also remind us of our place. The filaments existed for millions of years before humans evolved. They will continue existing for millions of years after human civilization ends. They are not for us, not designed for our comprehension. They simply are. Products of natural processes operating on cosmic scales with no concern for whether earthbound observers can understand them. The universe does not owe us explanations. It does not simplify itself for our convenience. Reality is as complicated as it needs to be, and sometimes that is very complicated indeed. The filaments glow in frequencies invisible to human eyes. We detect them only through instruments, radio telescopes, invented within the last century, used to study the galactic center only within the last 40 years. For all of human history before that, the filaments were completely unknown, unguessed, unimagined. How many other structures exist that we have not yet developed the tools to detect? What else is out there, glowing in frequencies we do not observe, organized by principles we have not conceived, revealing aspects of the universe we cannot currently comprehend? This is the deepest implication of the filaments. They prove that the universe contains surprises, fundamental features of reality that remain hidden until technology advanced sufficiently to reveal them. And if Meerkat could reveal something as dramatic as 1,000 magnetized threads stretching through the galactic center, What will the next generation of telescopes reveal? What impossible structures will turn out to be commonplace? What mysteries will replace the ones we partially solve? The filaments are a reminder that we are still discovering basic facts about our own galaxy. Not exotic physics in the early universe, not speculative phenomena in distant quasars, but structures in the Milky Way, 26,000 light-years away, in our cosmic backyard. If our understanding of our own galactic center remains this incomplete after a century of radio astronomy, how much do we really know about anything? How confident can we be in theories about galaxy formation, dark matter distribution, or the evolution of the universe, when we still cannot explain one-dimensional magnetic structures in our own galaxy? The filaments stand as monuments to our ignorance, visible signs of processes we do not understand. Every radio map of the galactic center is a portrait of mystery. Every observation a reminder that reality is stranger than our theories predict. The threads glow, they persist, they defy explanation. And they will remain long after we are gone, marking the heart of the galaxy with invisible light that makes magnetic field lines visible. Cosmic strings in the truest sense, not topological defects, but literal threads of enhanced magnetic field and cosmic rays, stitching together the core of our galaxy in patterns we are only beginning to read. Right now, as you finish hearing this, those threads are still there, still glowing, still stretching through the darkness at the center of our galaxy. They have been there since before your species learned to walk upright. They will be there long after your civilization crumbles to dust. They are not waiting for you to understand them. They do not care whether you ever do. 26,000 light-years from Earth. That is the distance. But distance is not the barrier. Time is the barrier. The light you would see from the filaments tonight was emitted 26,000 years ago. Before agriculture. Before cities. Before written language. When the photons began their journey, your ancestors were nomadic hunters. By the time those photons reach your eyes, if you had a radio telescope instead of optical sensors, those ancestors had invented civilization, built empires, developed science, and pointed instruments at the sky to detect the ancient light finally arriving. But the filaments you would observe are not the filaments that exist now. Now is meaningless across such distances. The present you experience and the present at the galactic center are separated by an event horizon of causality. What happens there now will not affect here for 26,000 years. What you observe there now happened when mammoths walked Earth. Time and space conspire to isolate us. To prevent direct knowledge of the galactic center's current state, we are always looking at ghosts, echoes, historical documents written in radio waves. The filaments teach us that the universe operates on scales that dwarf human significance. 150 light-years. That is the length of the longest structures. To traverse one filament at the speed of light, the fastest speed possible requires 150 years. No human civilization has lasted that long in any recognizable form. The Roman Empire rose and fell in less time. The entire industrial era, from steam engines to spacecraft, spans less than 300 years. The longest filaments are structures that light itself takes longer to cross than all of recorded human history, and they persist for millions of years. 6 million years is the age estimate. 6 million years ago, the Miocene epoch. Your lineage had not yet split from the great apes. There were no humans, no genus Homo. Just primates in African forests, unknowing and unimportant, while at the galactic center, something was organizing magnetic fields and cosmic rays into threads that would glow for longer than it took your entire species to evolve. From those primates to the technological civilization now detecting the ancient light. The mass energy in a single filament exceeds 10,000 suns. Not the energy those suns produce over their lifetimes, their total rest mass energy. E equals mc squared. Matter converted directly to energy with perfect efficiency, contained in invisible magnetic fields threaded with particles moving at 99.9% of light speed. One filament, of which there are hundreds, thousands, pervading the galactic center, each one a repository of energy sufficient to power human civilization for billions of years. And we discovered them by accident. Yousefzadeh was looking for supernova remnants. He found something else entirely. Something that should not exist according to theory. Something that challenged fundamental assumptions about plasma physics and magnetic field stability. 40 years later, after Meerkat revealed 1,000 more, we still do not understand them. Not really. We know what they are made of. We know approximately how old they are, but the mechanism that creates them, the reason they adopt their impossible geometries, the process that maintains them for millions of years, these remain mysteries. This should disturb you more than it probably does. We live in a technological civilization. We have sent probes to every planet in the solar system. We have split atoms. We have sequenced genomes. We have built machines that think. We believe we understand the universe. We teach physics in universities as settled science, established laws, known principles. And yet we cannot explain one-dimensional magnetic structures in our own galaxy. Structures we have been observing for 4 decades, with increasingly sophisticated instruments, getting better data every year, and still failing to achieve complete understanding. What does this say about our other theories? Our models of dark matter and dark energy are based on observations far less direct than radio maps of the galactic center. We have never detected a dark matter particle. We do not know what dark energy is. We assume they exist because the alternatives seem worse. But if we cannot explain structures we can actually observe, structures made of normal matter and known physics, how confident should we be about invisible components we infer only indirectly? The filaments prove that the universe contains complexity we did not predict. Meerkat revealed them not because theorists suggested they should exist, but because the telescope was sensitive enough to detect them. They were a surprise, a discovery, not a confirmation. This is how science actually works, not through logical deduction from first principles, but through observation revealing phenomena that theory must then scramble to explain. And sometimes, theory fails. Sometimes, reality is simply more complicated than our models can accommodate. The magnetic field in the galactic center is not a simple dipole. It is not a uniform background. It is a tangled, hierarchical, multi-scale structure, with filaments embedded in sheets, embedded in loops, embedded in the large-scale field shaped by galactic rotation. At every scale, new complexity emerges, new structures appear. The more carefully we look, the more detail we see. There is no evidence this complexity bottoms out. No indication that some finest scale exists where everything becomes simple again. Reality may be fractal, complex at all scales, turtles all the way down. This fractal complexity defeats human intuition. We want simple explanations, elegant theories, beautiful equations, and sometimes we get them. General relativity is beautiful. The standard model of particle physics is elegant. But these theories describe idealized systems, exact symmetries, simplified configurations. Real astrophysical environments are messy. They violate symmetries. They involve multiple physical processes operating simultaneously with comparable strengths. No single process dominates. No simplification applies. You must account for gravity and magnetic fields, and turbulence and cosmic rays and radiation pressure and thermal pressure and rotation and shear, all at once. The equations become intractable, numerical simulations become necessary, and even simulations struggle when the dynamic range is too large. When the fastest timescales differ from the slowest by factors of billions, when the smallest length scales differ from the largest by comparable factors, the filaments exist at the intersection of all these complexities. They are not simple. They cannot be understood in isolation. They couple to everything else happening in the galactic center. To understand them fully would require understanding the entire ecosystem. The supernova rate, the star formation history, the accretion history of Sagittarius A star, the initial magnetic field geometry, the turbulent cascade, the cosmic ray transport. Every factor matters. Remove one, and the whole picture changes. This is not a problem you can decompose, not a system you can study one piece at a time. It is irreducibly complex, and we are trying to understand it from one snapshot, one moment frozen in time, observed from one angle. with incomplete information. The honest assessment is this: we will probably never fully understand the galactic center filaments, not in the sense of having a complete quantitative theory that predicts every observed property from first principles. The system is too complex, the data too limited, the time scales too long. We can build models that capture some features, explain some observations, make statistical predictions about filament populations. But a complete explanation, where we can say with certainty exactly how each structure formed, why it has its particular properties, and how it will evolve in the future. That level of understanding is likely forever beyond reach. This is the tragedy and the triumph of observational astronomy. We discover wonders, map structures, measure properties, but complete understanding remains elusive. We see through a glass darkly, catching glimpses of processes operating at scales vastly larger than ourselves, over durations vastly longer than human lifetimes, with energies vastly greater than anything we can produce. We are ants trying to understand a city, bacteria trying to comprehend an organism. The gap between our scale and the cosmic scale is almost insurmountable. But we try anyway. We build better telescopes, we develop more sophisticated theories, we train new generations of scientists who push incrementally forward. Each decade we know slightly more, understand slightly better. The gap never closes, but it narrows, asymptotically approaching some limit of knowability, determined by the nature of the universe and the structure of physical law. Perhaps that limit allows complete understanding, perhaps it does not. We will not know until we reach it, if we ever do. The filaments will outlast us. Long after human civilization ends, through nuclear war, climate catastrophe, asteroid impact, or simple demographic collapse, the filaments will persist. Still glowing, still stretching through space, still organized in patterns we spent 4 decades failing to fully explain. They will not mourn us. They will not notice our absence. They are not conscious, not alive, just configurations of magnetic field and cosmic rays following physical law. Indifferent to observers, existing because the conditions allow it, vanishing when conditions change. No purpose, no meaning. Just structure emerging from chaos, complexity from simplicity, order from randomness. This is the deepest lesson of the filaments. The universe does not need observers to contain structure, to organize itself into patterns, to create beauty and complexity. It does this spontaneously, automatically, through the blind operation of physical law. Humans are not central, not necessary, not special. We are a brief flickering of consciousness in a cosmos that existed for 13.8 billion years before we appeared and will exist for trillions more after we vanish. The filaments glowed before we existed. They will glow after we are gone. And they will not care either way. We discovered hundreds of mysterious structures in the Milky Way's core. We cannot explain them. Not completely. Not yet. Perhaps not ever. They stand as proof that reality exceeds our grasp, that the universe contains more than our philosophies dream of. That mystery remains even in our cosmic backyard. 26,000 light-years away. Close enough to study in detail, far enough to remain forever strange, the threads that bind the galactic center together. Invisible strings making music we cannot hear, playing notes that last millions of years, in frequencies our biology cannot sense, for an audience that does not exist. Because the universe needs no audience, it performs for itself alone. If this leaves you uncomfortable, sitting there in the darkness, contemplating invisible threads at the galaxy's heart, good. You should be uncomfortable. The universe is not designed for your comfort. It is vast, violent, ancient, and utterly indifferent to whether you understand it. The filaments are just one example, one structure among countless others, all glowing in frequencies you cannot see, operating on scales you cannot intuitively grasp, following rules you partially comprehend. The mystery is not a bug, it is a feature. Reality is fundamentally mysterious. Science reveals more questions than answers. Every discovery opens new puzzles. And that process never ends. The threads are still there, still glowing, still waiting. Not for you, just waiting. Because that is what magnetic structures do in the presence of cosmic rays. They glow, they persist, they exist. And we watch from our tiny planet orbiting an unremarkable star in the galactic suburbs, 26,000 light-years from the action, trying desperately to make sense of radio waves that tell us something profound is happening at the center. Something we observe but do not fully understand. Something vast and strange and indifferent and real. If you want to explore more cosmic mysteries that challenge everything you thought you knew, smash that like button and subscribe. The universe is weirder than you imagine. And we have only just begun.